Okay, colleagues, why don't we start? We are already 2 minutes after our official time. Okay, hello everyone to the second block of the Marcel Grossman 2021 session BH5, Radio Astronomy from Space. We have two types of talks, which take half an hour including questions and 20 minutes including questions, so everyone knows how much time you have. I will warn you in advance, so 25 minutes after the start for a long talk and 15 minutes after the start for 20 minutes long presentations. So please stay in time so that we have time for questions as well. And the first invited talk today is to be given by Avery Broderick, Beyond the One Ring, Probing Space-Times with High-Resolution Millimeter VLBI. Avery, the floor is yours.
Thank you, Yuri. All right, so let's get this up and presented. Present. There we are. And try to get the Zoom controls out of the way. All right, I'm going to be talking about what we might be able to do in the future, really with a forward-looking perspective towards a very high-resolution millimeter VLBI, really space-based VLBI, and the implications for testing general relativity. A lot of what I'm going to be talking about is presented in this paper that you can find on the archive. The link is there. I'm just going to flip forward, but I assume the slides and certainly the recording will be available. And this is a paper that was co-authored with Paul Tita, Don Peshin, Roman Gold, all of whom are more junior and deserve a shout out. All right, so before we get on to the future, let's talk about where we are and how we've gotten here. Gravity tests from horizon scale imaging, the story that we try to sell and have been selling for the past decade. So I think on Monday, there were two talks on the polarization results. And of course, before the polarization results, we had the first image result. And while there's a lot of exciting elements to that image, for gravity, it really came down to putting a ruler across the image, measuring its size. And we had a number of ways that we tried to do that, from geometric modeling to direct accretion flow modeling to image feature extraction, a sophisticated version of putting a ruler across the image. But at the end of the day, it was all about measuring the size of a ring. Moving towards the future, and something that is actually quite old now as a concept, is to do more detailed astrophysical modeling with parametrized underlying accretion flow models. Here's a picture that I used to show where we have a cartoon for a thick disk with a jet, and we have a semi-analytic modeled image that has the key characteristics that we expect in any image of a black hole: a shadow and special relativity imposing itself, the dynamics of the gas imposing itself with a brightness distribution. Of course, that shadow and the shape of that shadow provides some information about the underlying space-time. And I believe there were talks on Monday, and there'll be later talks today. I'll put little statements of other talks to see that are relevant for this, for whatever I'm talking about down at the bottom. So please do pay attention to those as well. But there's the shape of that photon ring has long been highlighted as a potential observable for gravity. Of course, once you put emitting material on there, the dynamics and the imposition on the dynamics of the gas also shows up and has potentially interesting impacts, gives us additional leverage, but also additional problems with the astrophysical uncertainties, things like how fast is the gas actually rotating about the black hole, how thick is the disk, etc. Nevertheless, there is a bright future for these sorts of methods. Here's a test that we performed a few years ago now, where simulated data was generated from a dynamical simulation and produced and was fit with one of these semi-analytic models, and it produced a fit image that actually looks quite a bit like the average image from the GRMHD simulation, and even accurately reconstructed elements of the space-time. And looking even further into the future, the idea of measuring dynamical events or detecting dynamical events and trying to reconstruct the dynamics in addition to the static structure of the space-time really opens up opportunities to tomographically map spacetimes, make spin measurements that are making use of the fact that the dynamics separate in time what is difficult to separate spatially along the ray trajectory if we have only a static image. And example analyses of these have produced very precise constraints on the underlying spacetime. And there's a paper by Paul Tita that explores this. And at some level, the rest of my talk is an attempt to understand the unreasonable success of these sorts of analyses. And I'm going to do this from the perspective of a specific challenge. How might we measure the spin of M87? And that's a challenge that's uniquely hard. And it's hard because the kinds of methods that I already described, measuring the size, each one of them has a associated complication. So measuring the size as a means of measuring something about the underlying spacetime as a test of general relativity or as a measure of spin requires a simultaneous measure or an alternate measure of the mass from some other means. So something like the stellar dynamics mass. And that has to be done at the same precision that you would like to make a spin measurement. And so that simply doesn't exist now. So that's perhaps not the immediate way forward on M87. A second might be measuring shapes, but M87 is viewed almost directly down the polar axis. And so all black hole shadows shapes are circles when we're looking down the axis of symmetry. So even though a great deal has been made about measuring shapes and asymmetries, for M87, it doesn't really look like that story is relevant. And then all of this astrophysical modeling sounds great, and I'm happy to beat that drum, but it is always susceptible to concerns about uncertain underlying jet physics. If we don't really understand the astrophysics, how do we understand the gravitational physics after trying to remove it? That is to say, what's your prior that general relativity is wrong or astrophysics is wrong? And I think everybody, even the most gung-ho among us, admit that astrophysics is less certain than gravity. Now, there are ways that we might push forward with measuring gravitational features. And one that I just want to mention as a proof of concept is something that we call affectionately themaging. It's really a Bayesian image reconstruction scheme that merges modeling and imaging. The idea is to lay down some non-parametric model. And my understanding of what non-parametric means these days is just it has many, many parameters that are not physically motivated. And this is really a forward modeling approach, but it's one that's injected or mated with all of the model comparison technology that we have built. And so that means we can do all the standard model stuff, like make triangle plots and compare correlations between pixels, assess the reality or the significance of a feature in an image, and construct posteriors, in fact, on the images altogether, develop some sort of uncertainty. And once you can play that game, you can do things like add geometric features to the image. So use the image to reconstruct all of the uncertain structure that you don't have a prior expectation for, and you use a geometric model or some other physically motivated model to reconstruct the stuff that you think you have a reason to expect. So for example, adding a ring. So here's a number of GRMHD images that were produced for M87 as part of the M87 image library. And in each of them, you see a prominent ring-like structure. I'm not going to opine yet on where that comes from. And we can imagine fitting the diffuse emission with an image and the ring with a ring, and that's the result. So I can blink back and forth between these, and you can convince yourself that the rings are in fact picking up those ring-like structures. And in fact, they're doing it quantitatively well. Here's a picture that shows the intensity profile in blue and the posterior on those ring feature radii. The green bumps, the green posteriors, live within that spike in the blue associated with the high brightness feature. Okay, so we have the capacity not to image the ring, but to detect the ring in this way and extract quantitative information with high fidelity about it in principle. And so this is something that we would like to try in the future. But it does raise an immediate question. Which ring are we looking at? And what is this related to in the space-time? How do we relate this back to the underlying space-time properties? And here was a nice figure from Johnson et al. 2010. I think it was made by George Wong, that took a GRMHD simulation profile and identified which portions of that profile came from different order rings. And so the n equals 0 is, I'm going to call, the direct emission or the primary image. So that's kind of an abuse of the order of the photon rings, is this bottom hump. But then on top of it, there's this sequence of higher and higher order images, which of course is goes off to infinite order. And at each one, the peak is shifted by some amount. And so we really have to think a little bit about how these different rings are going to be related to each other. I will note that there's, of course, always the prospect for interesting polarization physics. Stay tuned. There are a couple talks in this section about exactly that. Now, again, I'd like to note that this is really, everything old is new again. Here's a movie from a long time ago that shows orbiting features. And in it, you can see very explicitly all of these higher order images, these primary, secondary, and tertiary images, or n equals 0, 1, and 2 ring structures, shown from first along the axis and then at oblique angles. And so this idea of measuring something about the space-time by looking at the structure and relationships between the higher order lensed images and the underlying ring, has kind of always been the story, but it has been obscured, I think, by the reliance or the relevance of the astrophysical aspects of the emission region. Okay, so now I want to synthesize or remove that astrophysical part of the discussion and just focus on the gravitational piece, returning towards the end to the actual astrophysical application. And so the picture that I'm going to have for this is we're going to have a bright ring of emission located at some radius, and that's going to produce a multiple sets of rings. We'll have that primary hump, that's the photons that came directly to us, the secondary image, the tertiary image, and then you can keep going down that list if you like. So this is the picture of the emission region that I want to think about as an idealization of M87 and ask, what could we say if this were the case, and then relax it slightly. That is to say, measuring spin is really going to be this lensing measurement and comparison, quantification of the difference between different lensed order rings. So where are these coming from? I've already alluded to this. If this ring of emission is being viewed now in a slice perpendicular to the equatorial plane and the symmetry axis, so the observer in each of these plots is off at the top at infinity. The emission from the ring that comes directly to us, that is, it doesn't go around the black hole at all, is what I've been calling this direct emission, or this n equals 0, and it's shown by the solid lines. The first lensed image, or the secondary lensed image, is the dashed line, and it makes a trip around the back of the black hole before it comes to us. The tertiary goes all the way around the black hole before coming to us. And each of these will appear at a different location on the observer plane. The hierarchy is dependent upon the location of the emission region, and it's dependent upon the spin of the black hole, the gravity of the space-time associated with the black hole. It is the n equals infinity order that defines the edge of the shadow, and there's no condition that says that these have to sit outside of the shadow. So in fact, we can have rings that appear inside the shadow, depending upon where exactly that emission region is. All of this, again, is just for a polar observer. If you were to change the inclination, of course, it would change the story, and we'd have to think about it. So if we were going to try to be quantitative about it, we could draw some mapping between where that bright ring of emission was, the spin of the black hole, and where these different order features appear. And that's shown in these three pictures. So on the left, we have that direct emission or that primary image. And we see what we already knew, that the primary image location is really dictated by where the emission is. I can make an arbitrarily large primary image ring by making an arbitrarily large emission feature. Now, you might argue about the physical relevance of such a feature, but certainly there's no limit to how big I can make it. On the other hand, if we go all the way to the tertiary, by this point, changing the size of the emission region doesn't really affect the location of the tertiary very much at all. It's almost completely dependent on the underlying space-time, on the spin. And the secondary, the n=1 ring, is a mix of the two. And so I might say that this n=0 ring, or the primary image, is really a measure of astrophysics. And then as we go to higher and higher orders, we're increasing the dominance of gravity. And n=1 is sort of in between. Another way to look at this sort of fact is to look at where the n=0, where the primary emission radius would appear versus the secondary emission radius would appear, where the n=0 ring and the n=1 ring would appear on the sky, as a function of where the emission radius really is. So there's some minimum size for the primary and secondary that comes from placing the emission at the black hole horizon. So that terminates this curve. But then as we move outward in emission radius, this curve extends to ever larger primary radius and, in fact, to an asymptotic secondary radius. And the location of this curve depends upon the spin. And I've normalized everything by the mass. So something that's actually quite important is that while a single mass and spin pair is degenerate in the sense that I can traverse it with the emission radius, different mass spin pairs produce different curves. They are not renormalizable onto each other. And that's exhibited by trying to renormalize the mass for the spin 0.998 and 0.75 curves onto the spin 0 curve. So in this case, I think that we kept the, we did the renormalization to try to make them cross at some convenient point, but you can see that just by renormalizing the mass, just by stretching them in the two directions, it's not possible to make these lie on top of each other. And that lack of degeneracy is an important consequence or important effect. So it's going to be related to something that's going to allow us to uniquely estimate the mass and spin using the relationship between these rings. Of course, you could do this with the secondary and tertiary images as well, and they exhibit this very different feature of having a terminus. There is a maximum secondary size. There is a maximum tertiary size. And that means that the first gravitational impact of having measured them is that you completely eliminate, or eliminates the wrong word, you completely bound the impact of the astrophysics on the mass constraint in something like M87. So if we were to actually measure the n=1 ring, there's a fixed maximum relationship between the size of that ring and the mass in angular units in m/d. Okay, and that's not the case for the n=0 ring, that primary emission or the primary image, which again, we could have a pathological underlying astrophysical system that has a very large ring potentially. And again, you might make physical arguments against it, but any such pathological situation would not produce an arbitrarily large n=1 ring. So that bounds the uncertainty. And a similar story for the tertiary. For the n=2 ring, you'd again see a bounded range now dominated by the spin uncertainty. Now, before I continue, a word about detectability. I have two concepts of detectability. There's imaging, that's resolving it, placing at least one resolution element across it, and detecting it, something like this hybrid modeling imaging business, where we have some parametric estimate of the properties of the ring, but we can't actually produce an image with multiple resolution elements. Typically, that can detect features that are about an order of magnitude smaller than the ostensible diffractive scale if we have similar sensitivities as the EHT. So I don't want to sugarcoat this. If you want to resolve that primary image ring width, not identify the existence of it, not measure its radius, but actually resolve its width, we're talking about resolutions of 5 microarc seconds. If you want to see the secondary, 1 microarc second. And if you want to see the tertiary, another factor of 10 to 20, maybe 0.05 microarc seconds. So this is becoming progressively more difficult. They're getting more narrow, they're getting dimmer. Okay, so the challenge is non-trivial. I think n equals 0 and n equals 1 might be doable from Earth as a detection. Imaging probably requires space VLBI just for those. And the tertiary will almost certainly require lunar-sized orbits just for detecting, not imaging, but I would be happy to be proven wrong on that. So given the extraordinary resolutions we're talking about, this really is, in some sense, very futuristic, comparing to 20 microarc second diffraction limits for the EHT. Okay, so how do we make this mass spin measurement from detecting the n equals 0 and n equals 1, the primary and secondary? That's, remember, the photon that came to us and the photon that went around the back of the black hole before coming to us. The key is this non-degeneracy between these two curves. If we have either looking at them in the angular radius plane or parameter space, or in this case, we're looking at them in the mass spin parameter space at fixed angular radii, but with different emission radii. Okay, so we've put the ring of emission at different locations. So in the blue case, it's at 2m, and at the red case, it's at 6m. Now, again, there's a degenerate curve here in that it's being traversed by the location of the emission radius. When I say it's at 2m and 6m, that gives us the point up here where they cross. But if I only had the angular sizes associated with that for this blue curve, they would traverse this entire path. And so I'd have a degenerate constraint in the mass spin space. But as soon as I have two measurements, and assuming that the underlying source is variable, and all of the EHT sources are variable, right? So Sagittarius star is certainly variable, M87 is variable, albeit on somewhat longer timescales. Then these two degenerate curves are not degenerate with each other. There's one location where they cross, and that location where they cross is exactly what yields a mass spin measurement. And something kind of nice about this is, well, the mass is going to depend upon the distance to the object, right? We only measure an angular version of the mass, m over d. The spin is constructed entirely from angular ratios. So it's independent of the distance. So we might get to a point where we could have a higher precision spin measurement than mass measurement for something like M87. If it varies so that we can make two measurements, we can imagine easily making three measurements. And going from 2 to 3 takes us from a measurement of spin to a test of general relativity. And I would liken this to the binary pulsar tests, where you have many ways of measuring the same thing, and you want to see that they're consistent. In this case, we're not measuring the mass of two components in a binary, we're measuring the mass and the spin. Those two things should be consistent across the any observation periods of relevance for the EHT and beyond. And in that case, there is a unique answer that we should be obtaining in this mass spin parameter space. So this provides, in principle, a way to look for consistency with GR. A deviation, I don't know what it necessarily would imply, but we can get an idea of what kinds of deviations we might expect. And so here's two versions of these constraints in the mass spin parameter space that comes from looking at an image produced from a Kerr-Newman black hole. So the details of what that is aren't even important. It's that there is a parameter that deviates away from general relativity, Q, the charge. And this charge, when it's around 30% in some dimensionless units, is big enough that we could detect it with the kind of precision that we think we could get from Earth with these detection measurements. Okay, so already 3 epochs of observations, maybe not the EHT, maybe the NGHT, might be able to say something. If we can image these, of course, these would be far stronger statements. But what about the tertiary? What about that n equals 2? So I don't want to sugarcoat that. It's going to be hard. So the measuring the n equals 2 means we're really probing very small scales, really have to be looking at space-based detections, not even space-based imaging. But what you buy immediately for that is breaking this degeneracy in a single observation. So we don't actually have to observe in multiple epochs and hope the underlying sources change the location of the emission region. We can observe the underlying source only once, combine the n equals 0, 1, and 2 size constraints, and produce a constraint on spin in a single epoch.
Every 2 more minutes.
Thank you, Yuri. Okay, and that's shown here by this orange contoured region. The blue contour region is the standard n equals 0, n equals 1 degeneracy curve with this high precision, and the orange contour is what happens if you combine it with the n equals 2 ring radius. You can play the same game testing general relativity again. Again, we have many curves that all have to cross at one point. In principle, the n equals 1 and n equals 2 curve doesn't tell you any new information. So for a test of GR, again, we have to appeal to a variable source. We have to look at the source at 2 different times with the emission radius at 2 different locations and compare what we see in those 2 different instances. But I just want to draw your attention to how much smaller this deviation parameter has become. It's gone from 30% to 1%. We could tell apart handily if we could detect an n equals 2 photon ring and the others. Now, of course, that was that idealized picture. There's a lot of real complications that we might have to worry about, things like radially distributed emission, non-zero disk heights, optical depth, inclination, asymmetry. And very quickly, we find ourselves just moving back towards this modeling approach where we model the astrophysical emission region and extract the multiple lensed images. And this is really a crystallization or a sharpening of the argument that's at work there. But if we relax just the ones that I haven't highlighted in red, the radial distribution, disk height, and optical depth, it turns out that the stories are all very similar. You can read the location of the different photon rings off the images and plug them into the same sort of analysis that I was showing results from for having a known radius measurement, and pick out then a spin and a mass that depends, of course, on the precision with which you think you're really able to do this. Okay, so these are with precisions that are similar to what we could do pulling them off of those images. So it is a similar story. I don't think that this is overly complicated by the addition of more realistic source structures. So here's the summary. I hope I communicated that detecting photon rings is within reach, that we have sophisticated algorithms ready to be deployed now, and those can leverage long baselines to push to even more extraordinary resolutions. Multiple ring detections is really a lensing measurement, and that lensing measurement provides an astrophysics insensitive probe of the underlying space-time. And when we can see the primary and the secondary, so the direct emission and that n equals 1 photon ring, which is potentially detectable from Earth, but must be imaged from space, we have a degenerate mass spin measurement. And 2 observations give us mass and spin independently. 3 would give us a GR test, potentially up to 30%. In the far future, with a space-based array, lunar-sized space-based array, we may be able to detect the tertiary as well. And that would give us immediate constraints on mass and spin. And 2 such measurements would drive those GR limits down to roughly 1%. Thank you.
Thank you very much, Avery. Colleagues, we have time for one question or comment. Please go on. So you can either speak up or who was the first? Yes, Aditya, please go on.
No, I think Volker was first. It's fine.
Okay, well, go on.
So may I ask a question?
Yeah, please go on.
Okay. Yeah, you mentioned that there might be images inside the shadow angular radius. For that, you would need light sources between the horizon and the photon region, right? I would like to hear your opinion. Do you think there's a realistic chance to ever observe something like that?
Well, so that's first, it is certainly possible to see foreground emission, but that's not what I'm talking about. So you can see this case has a very compact ring. The ring is outside the horizon. It's I think right near the ergosphere, but the lensed image ends up being inside the shadow. And the reason for that is if we go to, we only need one of these plots that show the trajectories. You know, this red trajectory is similar to the case that I was showing you a moment ago. This photon would certainly be captured by the horizon, but not before crossing the equatorial plane. And so equatorial plane emission is all you need in this case.
Okay.
Thank you. Aditya, why don't you ask your question, and Avery will try to ask it in not more than 20 words. But we'll see how it goes.
I think chat seems to be a better option. I have a lengthy question. It's fine, no worries.
All right, thank you.
So our second speaker today is Andrew Chell. He will present the talk on the inner shadow of the black hole in M87, a direct view on the event horizon. Andrew, the floor is yours.
Is my screen sharing okay?
We see that you have started the sharing. Now I guess we are about to see your presentation. Let us wait a couple of seconds.
It's still black for me, and it's got the gray rectangles, I think, from Zoom.
How about now? Nope.
So Avery, while we are waiting, there are already two questions to you, and yes, it will take longer than 1 minute. So this was indeed a good suggestion that we use the chat for that. So Michael, do we want to try your option? Yeah, okay.
This issue where it worked the first time and then it doesn't work the second time.
That's all right, don't worry. And Andrew, I think that we all hear you fine right now, so you shouldn't worry about your sound while we are waiting for Michael to share his screen.
How's this look?
Great. Do you have I sent you an updated version. This is fine. Okay.
Is this the updated one? I can pull it if not.
Not the updated one.
Okay, give me just 1 second.
I'm sorry about this.
That's all right. It's always nice to use the most recent version.
This is the one you sent at 19 minutes ago at 10:45. Is there a more recent one than that?
Yeah, if that's the one I sent you last, just use it.
Okay.
Okay, so let us start. Andrew, I will give you a warning 2 minutes before the end of time, okay? I mean your time, not the time.
Yeah, thank you, Michael, for sharing the screen. Okay, and thank you all for having me here to talk about this paper that I did with Michael, who was sharing the screen, and with Alex Lupsaska, who talked Monday about the inner shadow of a black hole. So next slide. So this project sort of came, to me at least, from looking a lot at images like this one of simulations for the EHT. This is a typical sort of EHT simulation image of the black hole in M87, and we see a prominent shadow feature and photon ring, features I think we're familiar with from many of the other talks that we've heard. But I've been interested recently on several projects about what happens when you look at these images at very high dynamic range. Next slide. So one thing that is really evident when you go to high dynamic range, at least if you run the simulation for long enough and you use the right electron heating prescription, is that you can see a large extended jet similar to what we see in M87. So this is the case in these simulations, which I originally did for a paper in 2019, where you see the jet at several different frequencies. It's very wide. It looks a bit like the jet, or relatively like the jet in M87. And one of the things we're looking at is, how detectable will this jet be once we go to the NGHT, or even before the NGHT with improvements to the array, we should be able to start seeing this diffuse jet emission. So that's one aspect of this high dynamic range stuff. But next slide. But the aspect I'm talking about today is closer in, near the black hole. When we go to high dynamic range, we see things like the image on the right, where we see this extended jet emission surrounding the photon ring that we're familiar with. But we also see this sort of dark patch in the middle with very sharp edges. And I was worried about this patch, or confused about it at least, for quite a while. I thought it was maybe a consequence of some of the choices we were making in the simulation. But by investigating it with Michael and Alex, we came to the conclusion that this is really an important feature of the of GR in this system, and it's something that we could potentially measure with the HT. So next slide. So just a summary of this whole talk, this feature is what we call the inner shadow of the black hole. It's basically the direct image. So Avery introduced the sort of different orders of images. This is the direct image of the emission right at the edge of the event horizon, at least in the Kerr case. While this isn't a universal feature like the photon ring, it depends, for example, on the emission being equatorial and extending all the way to the horizon. It seems like many GRMHD simulations have the conditions necessary to make this observable. So I think there's a good chance we might be able to see it in M87 with future EHT or NGHT observations. And features of this image can be used to measure spin and inclination in a very similar way to what Avery was talking about earlier. And yeah, the NGHT will have the dynamic range and resolution necessary to observe this feature if it exists. So next slide. So now, just to review, what do we talk about when we usually talk about the black hole shadow? We're talking about this critical curve. So these two words are sometimes used interchangeably. The critical curve on the image plane separates rays that end on the event horizon with those that escape to infinity. So on the left, you see rays in yellow that escape to infinity, rays in black that end up on the event horizon. Some of them end up on the event horizon directly. Some of them wrap around the black hole a few times. But just the separation between these two sets of rays determines this critical curve. And the interior of that critical curve is what is typically called the black hole shadow. The shadow is really prominent, especially in images where the emission is optically thin and spherically symmetric, like this image on the right from a paper by Ramesh and Ryan a couple years ago. Next slide. So an alternate view, or I guess a complementary but slightly different picture comes from when we have emission regions that are not spherically symmetric, but instead confined to a region in the spacetime, for example, in the equatorial plane. So in this case, as geodesics wrap around the black hole multiple times, they encounter a discrete emission region again and again. And this gives rise to these a series of lens subrings that Alex talked about in his talk on Monday. Then these subrings approach the critical curve exponentially. Resolving these subrings again requires a spatially limited emission region. If the emission region is continuous, they'll just all blur together. But as Avery just talked about in his talk, if we can look at the different orders of these rings from the different numbers of wrappings around the black hole, we can use ratios of their radii and sizes to constrain features of the space-time and test GR. Next slide. Okay, so just to situate, again, this is a picture from Alex and Sam Grala's paper a few years ago, showing these different orders of images. So we have emission directly coming from the equatorial plane, and this m equals 0, and then we have m equals 1 from emission going around once, and m equals 2 from emission going around a full 360 degrees. Next slide. So this here on the left, I've broken up the different rays here by order. So you can see the red rays go around a full 360 degrees. The black rays hit the event horizon directly without crossing the equatorial plane once. So yeah, these rays are colored by the number of times they cross the equatorial plane, which in this case is the 17-degree line, like in M87, this green line. Next slide. And if we take these different collections of rays and map them on the image plane, we see outside of the sort of the center region, this this series of lens subrings that has been talked about before, approaching the critical curve, which is the yellow dashed ring. The images from these increasing number of crossings of the equatorial plane become narrower and approach the critical curve. But interior to this, there's a region that is colored black in this image, which comes from the fact that there's a set of rays that never cross the equatorial plane. So if the emission is confined to the equatorial plane, this region will be completely dark. And this is what we were calling the inner shadow. In between this region and the critical curve, which usually is denoted to mark the edge of the shadow, you can see that there are still rays that cross the equatorial plane. And this is what gives rise to emission inside the traditional shadow boundary, but outside what we call the inner shadow. And I think this is related to the last question that was asked. Next slide. Okay, so yeah, the basic point of this talk is that this is a high dynamic range feature. This is this inner shadow of this direct image of the event horizon. It shows up in a lot of these geometry simulations, even though it's not completely universal because it does depend on the details of the emission region. Next slide. So why in particular is this horizon image visible in these simulations? So I think when I first came to these simulations, I had the picture motivated, I think, by analytic work that led to them that these simulations were more like spherical emission regions. They were big, thick, puffy disks that mostly envelop the black hole in optically thin emission. But in this particular class of magnetically arrested disk simulations, which we've been looking into more recently, it turns out that the emissivity is actually predominantly equatorial as we approach the horizon, and it becomes actually quite thin, with the thinness of the emitting region seeming really to only depend on the resolution of the simulation. So if you look on the left, there's a picture of the emissivity throughout the simulation as we approach the event horizon. You can see that the emissivity is in the equatorial plane, very close to the event horizon, and it in fact increases toward the event horizon. So it becomes bright, and at least in the rest frame of the emitting material, the emissivity is increasing constantly toward the horizon and not peaking at some outer radius like at the ISCO or even further out. So this fact that we have equatorial emission and that it's extending to and peaking at the horizon is what is necessary to give us any emission at all at this inner shadow feature, at the edge of this inner shadow feature. Next slide. So here I'm comparing time averaged images from the simulation in the center column with images from an equatorial model. So the images on the left are coming from an analytic model that only has emission in an equatorial disk. And you can see the main point here is that these images look quite a bit the same. You can tune the equatorial disk model to look very similar to a simulation image, which I think is giving us another piece of evidence, in addition to the direct emissivities that we looked at, that the emission at 230 gigahertz that we're seeing is predominantly equatorial and can be really explained mostly with that model. There is a slight difference, which we can see in particular in the lower panels, which are showing the same image as the upper panels, but in a gamma scale, so accentuating high dynamic range features. On the right image from the simulation, there is a non-zero brightness in the middle inside this inner shadow feature, whereas in the equatorial model, it's completely zero there. This is because we are seeing some forward jet emission. We're seeing emission from the foreground, which gives the horizon image a finite floor in our simulations. Next slide. One thing in particular that I thought was really neat that came out of this is that this isn't limited to 230 gigahertz. I mean, we typically think of 230 gigahertz as an optimal frequency to look at these images of M87 and Sagittarius star because the systems are just becoming optically thin there. And indeed, if we go to 86 gigahertz on the right here, in the upper right panel in particular, that's a simulation image at 86 gigahertz, we see that we are starting to see optical depth obscure the image of the photon ring. But it turns out that this inner shadow feature isn't sensitive to optical depth, at least when we're talking about the optical depth of the disk material. So if the optical depth of the material in the equatorial plane can become large, but because this is a purely geometrical effect, we're just seeing the outline of rays that touch the horizon before crossing the equatorial plane once, and those that go to the horizon, that go to the equatorial plane outside the horizon. Even with relatively high optical depth, we can still see this feature very prominently in these images. Eventually, if we go to lower and lower frequencies, the forward jet emission will become optically thick, and then it will begin to obscure. But we're in this sort of intermediate frequency regime for quite a ways below the 230 gigahertz frequency. We typically look at The disk can become optically thick, but we could still see the outline of this inner shadow feature. Next slide. So this is just looking in profile across the image with 2 cuts at 2.3 gigahertz. The dotted lines are the analytic model and the solid lines are the simulation. And you can see the same floor at high dynamic range that I pointed out that's coming from the forward jet emission. And the main point here is to look at these 2 lines across the image where the top line is the EHT 2017 dynamic range. So in 2017, we said the EHT only has a dynamic range of about 10. We can only detect features that are about a factor of 10 below the peak of the brightness in the image. But the NG-EHT, which we're working toward building, should have the dynamic range of about 1,000. And so if the simulation is correct and how bright this feature is, the NG-EHT should have the dynamic range necessary to observe it. Next slide. So this is just a very simple image reconstruction showing on the left a simulation image blurred to the resolution of about the NG-EHT's resolution. In the middle, this is a 2017 reconstruction. So this is using a very similar procedure that we used to produce the first images of M87 from the simulation data on the left. And you can see that in the lower row of images, which are showing the high dynamic range, the simulation is putting a hole there, but it can't constrain the borders of that hole very well because we don't have the dynamic range necessary to detect the feature. But if we use NG-EHT coverage, where we're filling in a lot of different baselines, this is still all Earth-based, so we haven't increased the resolution very much, but we've increased the dynamic range substantially by adding many more stations and adding many more intermediate baselines. And then on the bottom right, we can detect this feature because we have the dynamic range necessary to produce faithful images down to about a factor of 1,000 from the peak brightness. Next slide. Okay, so I'm going to skip most of this second part of the talk, but basically just to say that the inner shadow images that I've been introducing, which I hope I convinced you could be detected with the EHT or NG-EHT in M87, provide another probe of space-time in a very similar way that Avery talked about in his talk. So the size and shape of the inner shadow feature change with spin and inclination in a predictable way. And so if we can observe and measure this feature, it can provide a second set of constraints on the metric from observations of the n=1 photon ring. So if we could detect both features, maybe with the combination NG-EHT plus space-based array, we could really, I think, start to put a lot of very tight constraints on the spin and then potentially on GR itself. Next slide. So let's skip this one. Skip this one, please. Yeah, so this is just showing different features of the lens horizon image. On the left is the one in particular I want to draw attention to, which is the radius. The radius depends mostly on spin at low inclination, so it can be used as a probe of spin if we know the mass. And in particular, the spin, the inner shadow size changes from about 40% from spin 0 to spin 1, which is a lot more than the critical curve or outer shadow, which I think is typically said to only vary by about 4%. Next slide.
2 minutes.
Yeah. Okay. Next slide. Yeah, so one thing we looked at in particular is if we have 2 curves in the image, we can measure these relative offsets. We can measure the ratio of their sizes. We can measure also the position of their centroids. So on the left, I'm showing the ratio of the shadow or of the inner shadow or lens horizon image size to the critical curve size, and you can see that varies with spin. On the right, and that's a map of sort of where as a function of spin and inclination, where the centroid offset between these 2 features exists. And in the paper, we provide some fitting functions to this. It turns out that, yeah, you can use all these features, the relative offset, the shift in position, and the ratio of the sizes to constrain the spin and inclination if you know, for example, the mass, or vice versa. If you know the inclination really well as an M87, you can use these features to constrain the mass and the spin. So next slide. So yeah, this will be the last thing I show. Basically, this is a very similar plot to what Avery was showing, this time using the critical curve, or you can say the n=1 photon ring as a proxy, and the inner shadow. So if we could detect both of these features and measure them, we could use their radii on the left and their centroid offsets on the right to determine constraints on the spin and mass if we know the inclination, for example. So this is an M87 case where we're assuming the inclination is fixed. You can see that the different bands represent uncertainties of 0.1, 0.5, and 1 microarcsecond, which I think is a reasonable range of errors for what we might be able to get with modeling with the NGHT. And on the left, you can see that that even at with 1 microarcsecond uncertainty, if we could measure both of the radii of both these features, we can constrain the spin pretty well and the mass simultaneously, even with this unknown mass. And on the right is showing the same measurement with the centroid offset. That only becomes really effective once we go to much smaller uncertainties. But this is a very toy example. In reality, we would throw all of these features and measurements into a modeling pipeline. We'd try to measure all these things. So I think this is just pointing the way that this type of measurement is possible. Next slide. And next slide. Next slide. Next slide. Yeah, so yeah, in summary, this feature of the equatorial event horizon is present in GRMHD simulations. It should be observable. It's not universal like the photon ring because it depends on the equatorial emission and the emission extending to the event horizon. But we think that many simulations have this present, and we could be able to say in the future with NGEHD observations, or I hope even with EHD observations in not too long, once we add more stations, whether or not we can detect this feature. And if we can measure it and start to constrain its properties, we can use them in conjunction with things like the photon ring to say things about the spin and space-time. So thanks, and I'll take any questions.
Thank you very much, Andrew. Colleagues, questions? I'll give you a few more seconds and then I'll ask my question. Okay, Andrew, okay, Darwin, please go on.
Actually, I have one question. You always refer to the image as image of the horizon. For me, I actually have a bit stomach ache because the horizon is something you can't really see. Basically, it would be just a region of non-emission. And I also have also one question. You always speak n=0 image and n=1 image from the emission close to the horizon. Could you elaborate what exactly does it mean?
Yeah, and that's a very good point. I think I'm being a little loose in describing this as the image of the horizon. I think if you had an infinitely bright source at the horizon, you can say what the direct image would be if you have a ring of emission right at this horizon. Of course, in reality, this will be infinitely redshifted. And so what I'm really saying is what does material that's very, very close to the horizon, where is that showing up in the image plane? Assuming it can emit brightly enough to start to overcome this very powerful redshift. So these, up to the purposes of the EHT or NGEHT resolution, or I think even much farther in the future, for the simulations we've looked at, these things are pretty indistinguishable, so we don't have to worry too much, I think, about exactly the offset of where the emitting material ends and where the horizon is. But yes, you're absolutely right that this is actually, I'm talking about in the images that we're seeing, this is actually emission from material very, very close to the horizon, not directly on the horizon where it would be infinitely redshifted. And by n=0 and n=1, I'm basically saying n=0 is our light rays that come directly to us without crossing the equatorial plane at all. So they come directly off the equatorial plane to us, whereas n=1 are images that cross the equatorial plane once. So they, for example, start on one side of the equatorial plane, go around the backside, hit it again, and then come to us. And then there's an increasing series of images, again, as in Alex and Avery's talks, where you go around and around the equatorial plane more and more times. And so that's where this series of images comes from.
Yes, thank you.
Thank you, Andrew. Let us move on. It's time for the next talk to be given by Alexander Zakharov, Shadows Around the Galactic Center and M87 as a tool to test gravity theories.
Do you hear me?
Yes, Alexander, we hear you fine.
Yes, okay, I could start.
Yeah, go on.
Thank you very much. I would like, first of all, I would like to thank organizers for nice opportunity to present this talk here. And in his talk, Avery said a golden sentence. astrophysics is less certain than gravity for this problem. So of course, naturally, we prefer to speculate about more certain issues like gravity. So, but this problem, of course, you know, your authors of this discovery, reconstruction of images for M87, it's like logo for black holes. But also there are two pillars for this kind of problems. One is synchrotron emission. Synchrotron emission was predicted by Isaac Pomeranchuk in 40s. And he got even a state prize for this discovery. Now you have numerous applications of this radiation, including astronomy, technology, and other fields. But also, you know, here I've reproduced two famous astrophysicists, Ginzburg and Shklovsky. They always emphasize that synchrotron emission, one of the main sources in many astronomical objects, including Crab Nebula, Sun, and other sources. But also, second pillar LBI idea was proposed by Matvienko, Kardashev, and Sholomitsky. It was also interesting idea, and was later realized in United States and other places. And now you are using this idea for Event Horizon Telescope. And now it's like logo, shadow is like logo for black holes, some key references, but also conferences, interaction of different people with different skill play important role. In general relativity, for instance, GR3 conference, you see here, you see Leopold Tinfeld, Vladimir Fock, and Roy Patrick Hare, who found this solution, namely at this period. And here you see Singh, famous Irish expert in general relativity. And also it's also interesting thing that experimental confirmation, astronomical confirmation of general relativity was discussed in lecture, plenary lecture by Vitaly Ginzburg at this conference. But Lumina paper was discussed also in previous talks. I will skip these details, but also this picture. But 20 years ago, Falke, Melia, Gol considered let us say, accretion in the framework of toy model, and they showed for millimeter band there is a chance to detect this black spot is like shadow, but in centimeter wave range it was not possible. Around 20 years ago, radio astronomy mission was under preparation, and Nikolai Semyonovich Kardashev, he was PI of this mission, requested to analyze fundamental or gravitational physics effects which could be observed with this facility. That is, let us say, poster of this mission. It was launched in 2011. It worked, but it's not visible. But the best angular resolution at 1.3 centimeter was around 7-8 microarc second. In principle, it was very good, even for, let us say, for M87 or for the Sagittarius A, but it was too long to detect shadow. So angular resolution was good, but by the way, its wavelength was too short, too long to detect shadow. But we discussed this issue as astronomical problem, and we published article. It's also connected with Chandrasekhar book. It's also Chandrasekhar book. Chandrasekhar considered critical parameters of impact parameter for photon geodesics. And here you see also he reproduced this picture in this his book. And if you have consider foreground sources, so in this case, observer could detect this kind of shape of, let us say, darkness. With darkness, we have to have darkness here. But of course, it's people you didn't know exactly mass of the black hole at the galactic center, but now we know that size of this shadow has to be around 52 microarc second and 42 microarc second for M87. But it's not the first reproduction of shadow. It was also showed in Bardeen paper earlier. And also it was, you see, if we consider this critical impact parameter, you see there is remarkable feature of this curve. So, and also it's reproduced here. Maximum value for either parameter is the same, it's 27, but position of maximum value depends on spin as 2a. And also every reproduce this picture for shadows. And you see for Schwarzschild case, it's well known, it's circle, it's with a radius square root of 27. But for extremely rotating black hole, you see in principle, you could evaluate spin if for ground sources showed us such kind of shadows. And even for position of observer at the polar axis, there is weak dependence of size of shadow as a function of spin. So in principle, in the distant future, probably it's possible to distinguish if people could reconstruct shadows. But for different position angle of observers and let us say intermediate spin value, so it's weak dependence on spin as a function of spin. But for extremely rotating black hole, so there is opportunity probably to detect this kind of spin. Since this title of this session is astronomy from space, we suggested to use radiostron and even future millimetron or other missions for such kind of experiment. And also we promote this idea to use this kind of facilities, space ground facilities, to resolve these shadows. But also, just for illustration, I borrowed these pictures from Melia website. Fulvio Melia also started this consideration more than 20 years ago. And here he simulated appearance of shadow in his computer. And here now we could claim that if people could detect this kind of shadow, position of observer is in equatorial plane, and also spin is very close to 1. So, and also a remarkable thing that if it is Reissner-Nernst metric, there is analytical expression of size of shadow as a function of charge. It's, for instance, that a Schwarzschild case, and dashed line corresponds to extreme Reissner-Nernst charge. If you increase charge, size of shadow is shrinking. But also, we did not believe that in astronomical conditions there is a charge. Like Jourdain said, for many years I have been speaking prose while know nothing of it. And also we are speaking about black holes in Randall syndrome theory or in beyond Hardetsky model. Why know nothing about this theory? Because tidal charge could be result of tidal charge or charge due to scalar tensor theory, which were proposed in the recent period. And also we promote this idea that shadows may be observed and resolved with millimetron mission. It's illustration of this our pictures, our papers on the subject. But also if there is a tidal charge, Q squared is negative. In these cases, the size of shadow is increasing. So in this case, it's even, but meanwhile, people suggested cases when there is a tidal charge with very small negative, with very huge negative value, significant negative value. It has to be rejected with observation for the galactic center because even at this period it was constrained with let us say precessor of Event Horizon Telescope teams. So that is also important thing that why it was no hope to detect shadow with radiostron, because radiostron we have to be here, but the shortest wavelength for radiostron here, so in this case scatter dominated source is expected. About now people could reconstruct shadows for different sources, but meanwhile people showing some artist pictures which are wrong, but they are very often published in many sources, including Nature magazine. So you see David Castelvecchi use it. But you see here, you see also appearance of shadow even inside accretion flow. It's a picture from interstellar. But if you truncate a disk, because it's not until ISCO disk, it was even in disk you could find appearance of shadow for these cases. And also in paper of Kip Thorne and co-authors, there is appearance, but it's very faint. It's secondary images, which were discussed at this also session by many authors. but also that is pictures of different images, but it's not new, of course, because it's Cunningham and Bardeen considered it many years ago in 70s, but also results of Event Horizon Telescope. I borrowed this slide 4 years ago. They presented this, let us say, observations, measurements. It's Fourier for Fourier transform measurements. It's after that we have to reconstruct images from Fourier transform, but it's in Russian literature we called it like incorrect problem because it's small uncertainties in Fourier harmonic could reproduce huge differences in result of image. So I will skip these details, but also result of Event Horizon Telescope, but also that is as a result 2 years ago. But also here I would like to repeat this picture about our paper about charge and black holes, because recently Event Horizon Telescope reproduced constraint on black hole charges with observations, because even now people could evaluate size of shadow for M87, and here you see blue line corresponds to size of shadow for Reissner-Nordström, but it's as it was calculated early, it was here you have to have 4, so like size of shadow in M units. Here, sorry, here this in this picture that is 4. So, and also you see that is also promotion of results of Event Horizon Telescope. You know it's very well. And also a remarkable thing that polarization of rings was observed. It was reported recently, and even magnetic field reconstruction have been done. That is conclusions, but I will leave these conclusions, and I will, because probably I have 1-2 minutes for discussion and question. Thank you very much.
Yes, thank you, Alexander. Thank you for this short review of what has happened during the last even more than something like 80 years. Colleagues, any questions or comments? While people think about their questions, comments, Alexander, could you please summarize from this brief review? So, what would be your takeaway message for us, especially within the radio astronomy from space session? So, what do you believe is the most important we should take from your talk?
2 things. First, in the future, with let us say space ground interferometry, probably people could evaluate even spin for M87, because every said that is hardly ever it's possible because it's almost face-on position. But even in this case, there is weak dependence on spin, because at the moment you see practically it's as I understood, for Event Horizon Telescope resolution is around 20-25 microsecond. It's of course it's too bad to resolve this, let us say, this size of shadow, and also there is a blurring because it's in this case it's impossible to catch this result. But as I showed, there is even Andrew showed in previous talk that there is a weak dependence of size of shadow as a function of spin for polar position of distant observers. And second, people suggested so many alternative theories of gravity, and many of them may be constrained even with current observations and current evaluation of, let us say, shadow size or corresponding ring, I don't know. As it was done, it seems to me a few months ago or a few weeks ago by Event Horizon Telescope team.
Thank you. Colleagues, any more questions or comments? If not, then thank you, Alexander. Let us move on.
Thank you very much.
So the next talk is to be given by Elizabeth Himlich. Elizabeth, please put your slides on. Universal polarization of the photon ring. I will give you a warning 15 minutes after you start. Thank you.
Oh, sorry. I'm here.
That's all right. We do see your slide.
Great. So I think it's working now, but I have had a couple issues with the PowerPoint thing. So if it stops, I'll just switch to PDF.
I'll let you know if something goes wrong. Yes, don't worry.
Okay. Thanks. So I'm Nina. I'm a grad student at Harvard. And before I start, I just want to thank Yuri and Michael for organizing this great session and giving me the opportunity to talk, and for the other speakers who've given great talks during the session. I'm going to be talking about the universal polarization of the photon ring, which is based on work done by Michael Johnson, Alex Lubsaska, Andy Strominger, and myself. And this came out last winter, but it's still generating lots of questions as we look toward taking high resolution polarized images of black holes and potentially using baselines extending to space. So this picture I have on my first slide is our favorite first polarized close-up image of a black hole released by the EHT earlier this year. And I also want to thank the Event Horizon Telescope collaboration. Hopefully looks like the slide is working. Which is a collaboration made up of hundreds of people from dozens of institutions around the world. And without all of their hard work, we wouldn't have these great images of black holes, and hopefully we'll have many more in the future. So thanks to the EHT, we can now take close-up polarimetric pictures of black holes, and we can all ask the questions of what do they show us and what can we learn from them. And in this talk, I'll just be focusing on one aspect of that question, which is how general relativity imprints a specific pattern in the polarization of light that's lensed many, many times around the black hole, and how we can measure that. And we can learn from it about both general relativity and about astrophysical properties of the black hole, as I'll explain. So going back to our picture, we have this ring of light around a central dark shadow. That's where the black hole is. And these streamlines reflect the polarization pattern of the light. This is a great first step. It's an amazing achievement, but we're hoping to go to higher resolution with radio astronomy in space. And then we expect to see something like the simulation. This one was done with adaptive ray tracing by Zach Gellis. And as people have explained in the other talks, it's striking that this ring is actually very thin, and it's made up of a series of even thinner rings that are piling up on the central critical curve. And this series of subrings has been called the Photon Ring. As again, it's been the subject of many talks here, so I'll try to review it quickly. So for my talk, I'll start with a review of what is the photon ring, and then I'll talk about what can we learn from its polarization. So the picture that I showed here, the previous slide, this is a total intensity image, but you can also imagine putting polarization ticks on top of it. And the polarization of the photon ring also has some interesting properties. And then also finally, I'll talk about how we can measure it. And before I get into this, I'll just give a rough outline of the answers and where we're going. So the photon ring, as has been reviewed already, is a series of exponentially narrow subrings, which are universal or matter-independent effects of general relativity that are present independent of the astrophysical accretion flow that's surrounding the black hole. And these subrings all have their own polarization, and the polarization pattern in the subrings actually encodes the black hole spin in a way that's also universal or independent of the matter surrounding the black hole. And then we can measure these subrings very well in Fourier space, actually, just essentially because rings of different sizes are well separated in Fourier space. And so the universal signatures in the image are also correspond to universal polarimetric universal interferometric or polarized interferometric visibilities in radio astronomy baselines. And we'll be able to see these signatures on long baselines extending to space. So if we measure the photon ring polarization, because it's universal, it will provide us a precise strong field test of general relativity in the strong general relativity around the black hole, and also will provide a measurement of black hole spin. So I'll begin with talking about what are the photon ring and subrings, and I'll just briefly review this to be self-contained. We've heard a lot about it in the other talks, of what makes up the black hole image and how we can describe it quantitatively. So when we look at a black hole, we can imagine looking from up into the sky or up onto an observer screen, and then setting up a coordinate system with Cartesian coordinates that we call alpha and beta, following Bardeen. And one of the unique properties of black holes are they're the only astrophysical objects that we know of that can trap light in bound orbits around them. And so when you imagine looking at a light ray that's shot back from where we are observing it into the geometry in the black hole, it can eventually become potentially bound around the black hole. If you ask what are the set of points on the sky or on the screen, such that when you shoot a light ray back from there, it will get bound, these set of points actually forms a curve, and it's called the critical curve. And because the Kerr geometry admits a range of radii at which photons can become bound in a fixed orbit, this critical curve is parameterized by radius. And conversely, we can think about a photon that starts on a bound orbit and then is perturbed slightly off of it, either outward or inward. If it's perturbed slightly outward, it will orbit many times and then come off to be observed. If it's perturbed inward, it will orbit many times and fall into the black hole, never to be seen. And the critical curve delineates the boundary between this type of behavior, as people have mentioned. And we can label the light that reaches us by the number of half orbits and that it makes around the black hole. And the reason why I'll care particularly about half orbits instead of full orbits, I'll get into later in the talk. So yeah, just as a review, the full image that we look at can be broken down into a sum of photons that orbit 0, 1, or 2 half orbits around the black hole. Most of the flux in the image is from this direct image, the n=0 image. But then there's an additional image from photons that undergo 1 half orbit and are lensed into this narrower region. And then the n=2 half orbits or 1 full orbit, which is lensed into an even further narrow region, et cetera, until it's cut off by some optical depth. And when we see this narrowing, we can ask how to describe it quantitatively in general relativity. And it turns out that the narrowing is exponential, and it's governed by an exponent that's universal in general relativity. So if we ask, if we have some distance to the critical curve of an image of photons that have undergone n half orbits, which has a width delta dn, we can ask what will the n+1th subring look like, and its width will be exponentially narrower than that of the nth subring. And this means that if we start with some direct image, which has delta d0, eventually, for the higher and higher subrings, they'll all sit on top of each other, or on top of the critical curve. And this means that we can approximate all the photons in the higher and higher subrings as being right on top of the critical curve and arriving at us with the same momentum and moving through the matter on the black hole with the same momentum, picking up the same emission. It's also important to note that this exponent gamma is only a function of the black hole mass and spin. And so no matter what astrophysical setting the black hole is in, no matter the details of the emission, we'll still see this same exponent gamma, which will, in principle, give us a way to look at the black hole's mass and spin. And this exponential narrowing of subrings has been verified in numerical simulations. And I think I'll end the review of it here, and then talk about how the subring polarization also universally encodes spin. And to do that, I'll first discuss how we describe polarization in Kerr, and how polarized light appears to an observer. So to describe polarization in Kerr, we'll start. Hopefully this is. Seems like my slide is not advancing. So
we see just the title. Yes, we see just polarization in Kerr and then everything white.
Okay, I think I should switch to the other thing because it seems to have frozen.
Okay.
Sorry about this.
That's all right, don't worry.
Let me just stop screen share. And hopefully I can start again. Okay. Just need to get through. Okay, can you see this?
We can see polarization in care, and then everything else is white. And so we see the titles.
Oh, still?
Uh-huh.
We see the curved black hole spin 0 less than A, less than 1. That's new, right?
Okay.
Yeah.
Yeah. Okay, I guess for some reason I can't see it in my other window, but I'll just go ahead if you can see it.
So Michael, you know how it should look like, right? So you can tell if it is not what is expected.
Well, do you maybe try advancing one more slide? Okay, yeah, now we see the black hole figure.
Okay, so it does look like it should. Okay, Nina, you're doing fine on time. Please don't worry, everything is great, and please just go on.
Okay, thanks.
Yeah,
Sorry
thank
about
you.
that.
No,
Yeah.
don't say so.
So, right, so this, you can't see the colored writing here, but that's okay. So our setup for describing polarization occurs that we're looking at a black hole with spin A at an angle theta O relative to the spin axis. And polarization is based on a photon momentum, P, and linear polarization, which I'll call F. And it obeys that F dot P is equal to 0, and that the polarization is parallel transported along the photon's trajectory. So the Kerr space-time has symmetries of stationarity and axisymmetry, and these imply that the photon's energy and angular momentum relative to the spin axis are conserved. And Kerr also has a Killing tensor from which you can construct this conserved Carter integral by contracting the photon momentum with the Killing tensor. And with these conserved quantities, plus the initial position of the photon in this initial direction of radial motion and of motion in the direction relative to the spin axis plus or minus theta, the photon's trajectory is entirely determined. Now, the actual geodesic through space-time doesn't depend on the energy of the photon. And so that sort of washes out, and we usually normalize L and Q by the energy. But instead of the energy, we have this other meaningful conserved quantity called the Penrose-Walker constant. And this is a sort of very special property of the Kerr space-time. It's denoted kappa. It's a complex constant, so we separate it into kappa 1 plus I kappa 2. And it's some combination of the components of the momentum and polarization that's conserved on the photon's trajectory. So this is extremely powerful because if you know the photon's position somewhere and momentum, and you know the Penrose-Walker constant for that geodesic, you can immediately read off the polarization without having to solve, the equation of parallel transport. So as an example of this, we can immediately read off the polarization on the screen given some photon with a certain arrival momentum and the Penrose-Walker constant. And this is the longest formula I'll have in the talk. So we have our Bardeen's green coordinates alpha and beta, and we can look at the components of the polarization on the screen, F alpha and F beta. And if we know the Penrose-Walker constant and the arrival location, we can just immediately read off the polarization, which is given here in terms of alpha and beta, the coordinates, kappa 1 and kappa 2, the components of kappa, and A times sine of theta O. So this is an extremely simple formula for the polarization. And the way that it encodes the spin here in A is what we'll use to extract the spin from looking at polarization in successive subrings. Okay, so also in order to think about how we can extract the spin from polarization, we need to revisit how the polarization depends on the even and odd parity of n in this large n limit. So I said before that in the limit of large n, we can approximate all of the photons as arriving on top of the critical curve with the same momenta and moving through the geometry in the same way, in the matter in the same way. But there's an important difference between even and odd subrings, is that they correspond to photons that have initial momentum direction flipped relative to the spin axis. So if we have some observer looking down the spin axis of a black hole, we imagine receiving a photon that underwent n½ orbits. It will have a different initial direction than one that undergoes n+1½ orbits, i.e. the initial momentum direction along the spin axis will flip between the n and n+1 half orbits. So the n and the n+2 half orbits will have the same initial momentum. So we can say that those will pick up exactly the same polarization in this large n limit, but the n and the n+1 subring will be different. So in isotropic emission, the intensity that we look at doesn't depend on the direction. So we can say that the intensity of the n and n+1 subrings is the same. However, the polarization is a vector quantity that depends on the momentum direction. For instance, in synchrotron radiation is proportional to P cross B, and this will just generically be different for the n and n+1 images. And just to get another physical picture of this, this is a picture by Angela Ricarte. If we have some magnetic field lines in the helical geometry around the black hole in an accretion disk, and we ask, you know, for the polarization of photons emitted and n and n+1 subrings, they'll just have a generic different P cross B. And that's what this figure is showing here. So here I'm plotting the photon subrings that are linear on a log scale. So they're exponentially narrow and exponentially close to the critical curve. And the green and purple ticks are the same for the n and n+2 subring and n+1 and n+3 subring. But generically, there's no relation between them in general relativity because they'll just have a different initial polarization. So we want to ask if it's possible to compare the n and n+1 subrings in these situations. And it turns out that there is a situation in which you can relate the n and n+1 subrings, and that's the situation of equatorial reflection symmetry, which actually is a symmetry of the Kerr space-time and is obeyed by matter distributions under time averaging. So it's a reasonable symmetry to assume. So under this symmetry, you can show that the polarization of the n and n+1 subrings are related in a universal way. And the relation is based on the fact that the Penrose-Walker constant is complex conjugated between these subrings. And that's essentially due to the fact that this initial photon momentum relative to the spin axis is flipping. So with this relation, you can then compare the polarization of the n and n+1 subrings. And I'll just put this formula for the polarization on the screen back here. So we can see that if you know, even if you don't know the value of kappa, if you know the relation between kappa and the n and n+1 subrings, you could use the polarization in the n and n+1 subrings to eliminate kappa and write down a formula that includes the spin. So if we construct these sums and differences of the polarization in the n and n+1 subrings, and then take ratios of its components, the Penrose-Walker constant will drop out, and you just get this relation for a sine theta O, which you can solve for if you know the polarization in the n and n+1 subrings and the position alpha and beta at which they arrive, which we're, again, assuming is at the critical curve in this large n limit. So this is a universal feature. It doesn't depend on what the value of kappa, which depends on the emission, actually is. It just depends on the spin and observer angle. And so if we know the observer angle from other means, this could potentially give us a way to extract spin from the image. Okay, so what I've talked about so far is just looking at the image, the direct, looking at it in image space, but in interferometry, we measure things in Fourier space. And so we can ask, what's the interferometric signature of these subrings and how much more resolution do we need to see them? And what's nice is that you don't even need to reconstruct the image potentially to extract spin. You can just use the visibility data directly. So yeah, I think everyone here knows probably that the HT uses this technique called very long baseline interferometry, which measures the Fourier components of the image along different baselines between pairs of telescopes on the Earth. And so like if that's like sampling one note of a song, and an important property of rings in Fourier space is that the Fourier transform of a delta function ring decays as an inverse square, but the Fourier transform of an annulus with thickness decays exponentially. So that means that if you're at some baseline length that's long enough to resolve the diameter of a ring, so long enough to know that it's there, but not long enough to resolve its width, the signal from that subring will dominate. And as soon as you start to resolve the width, signal will start to decay. Yeah, and that's what this figure is showing. So here we're fixing a baseline direction or baseline angle and looking at varying lengths. And the signal from, so n equals 0 isn't included here, but we're just doing a cartoon of n equals 1, 2, and 3. And the n equals 1 signal at first dominates, but at shorter baselines. But as you get to longer baselines, the n equals 1 signal, which is in black, starts to decay because you've started to resolve the width of that subring. But at those baselines, the n equals 2 subring, which is narrower, still looks like a delta function. And so eventually that's still decaying as an inverse square and will start to dominate over the exponential decay of n equals 1. And this will happen successively for the n equals 1, 2, and 3, et cetera, subrings, making them well separated in Fourier space. So we can extract their signal from looking at baselines of different lengths. And so the same here. So this is just another, I've sort of put roughly where we need to be to observe the different subrings, and we really will need space-based baselines to resolve the n equals 2 or n equals 3 subrings. And one good thing also is that the large n limit, as people have mentioned here, really includes even n equals 2, so we don't need to go really extremely far. We can go to these sort of Moon or Lagrange points, potentially extract universal features of general relativity. So just like the intensity visibility amplitude, which is what I showed you before, the polarized visibility amplitude has the same separation of the subrings in Fourier space. So what we measure in the polarized visibility amplitude is the Fourier transform of P, which is the sum of Stokes Q plus IU. And this is again a figure at fixed baseline angle. What we showed in this paper with Andy, Michael, and Alex is that given the polarized visibility amplitude, you can find two ways that it encodes spin universally, and you can extract the spin. One is from measuring the Fourier coefficients between even and odd subrings at many different baseline angles, so measuring some low Fourier coefficients and extracting the spin from those, or from fixing a baseline angle and measuring the ringing coefficients of these sines and cosines that you see in this figure for even and odd subrings to extract spin. And that latter one doesn't depend on the absolute phase information of the polarized visibility. So I think I'll wrap up here and just summarize what I've talked about. Sorry for the technical problems, but images of what I've said so far is images of black holes have a photon ring, which consists of a series of exponentially narrow subrings with a polarization pattern that encodes a spin. And they exist and are predicted to be polarized in this way universally in general relativity, so independent of the matter that surrounds them. And they can be resolved potentially by an extension of the EHT or the NGHT or some other radio astronomy effort to space. And if we have long baselines, we can see the universal interferometric or polarimetric signatures of the photon ring very clearly. And so if we measure the subring polarization, this will offer both a precise test of GR in the strong fields around a black hole, and also potentially a way to measure spin. So I'll stop there and happy to take questions.
Thank you very much, Nina, for the great review. Colleagues, questions or comments? We have 4 minutes for questions and comments. Finally, we have as much as 4 minutes. Okay, I will ask the first question. Yes, I will. Oh, okay, I'm late already. Okay, Valeria, go on.
Sorry. My question is about the possible observation of images large n. So in this paper, you spoke about a station at L2 in the Lagrangian point. But in principle, are there any barriers in extending a network of radio telescopes to larger distances within the solar system? So can you imagine to put a station at the 1 AU, for example, orbiting the sun, like Spitzer satellite, for example, which was a similar orbit as the Earth with an almost fixed distance. So in principle, can we imagine to do something like that and extend our network of space radio telescopes and explore the large n limit?
Definitely, yeah. I think, you know, having more resolution will enable you to see, well, at that long baseline, a larger n subring will dominate. I think one important thing here is a lot of these tests involve comparing successive subrings. So you need to have something that can resolve both, you know, the very high n subring and then the very high n+1 subring. So you need to have not just one satellite out very far, but you need to have satellites that are out at the right distance apart to measure to be where the n signal will dominate at one and the n+1 signal will dominate at the next one. But because the universal regime really does start around n=2, it's very powerful to have stuff even at the moon or at L2. We don't need to go all the way farther out to see that.
Okay, thanks. So there are no technical limitations in extending to longer distances. So
I'm not sure about the technical limitation. I guess maybe someone else on the call might know more about the technology.
Thanks.
Thank you. So allow me to go now, and then Alexander to you, and then we'll have to move to the next talk. So Mina, could you please go to your slide number 17? You have a number of slides, number 17, but okay, yeah. This one is fine. Thank you. So you have very wisely not shown the vertical axis of your plot. I mean the digits there. So can you please compare the amplitudes which you expect from this visibility, polarization visibility data? Is the amplitude which you expect comparable to what we get from Stokes I visibilities? Is it 10 times? Is it modeled to be 10 times weaker, 100 times weaker? So and how far the technology should go for us to actually measure it? Thank you.
Yes, I think I did. I have one of the plots does have the axis labels on there later.
Just tell me.
But yeah, so I think that, right. So you're asking about the polarization fraction of what we're looking at, and I think, yeah, we've seen that there's, you know, it's, you know, the polarization fraction is probably is low. I think but I think that we still are able to, I mean, get enough signal to make some reasonable measurements of the, you know, we have been able to look at the n=0, polarized visibility, and I think that if we are able to separate things well at these different baselines, there should be enough signal to look at them, but that's an excellent question.
Thank you. Polarized signal in visibility domain can easily be comparable to Stokes I, all right? So it's that was I was asking about the visibility space, because there it could be actually comparable. But we should probably go on. So if you get a number later, why don't you just put it in the chat so that everyone can see if it is expected to be comparable to Stokes I, or if it is indeed expected to be 10 times or even more weaker. Alexander, will you feel truly bad if you go on?
Yes. Short question, but okay, what is the source of polarization in your consideration? Is it synchrotron or another source? Because practically you did not speak about magnetic field and synchrotron emission.
Okay.
What is so?
Yeah. So yeah, we're imagining synchrotron radiation.
But in this case, what about structure of magnetic field?
You told me that it will be a short question, so please all follow up in the chat. Yeah, we have chat for that. Colleagues, I'm sorry, Alexander, don't feel bad. Please, all the follow-up in the chat, Mina, at least regarding the two questions which we had with Alexander, the two Russian questions. And let us go on right now to the next speaker. So Freak will discuss imaging and parameter estimation of supermassive black holes with the Event Horizon Imager Space VLBI concept. I will give you a note in 25 minutes, Freak. Go on.
Okay, thank you. Yeah, so we have all seen this very nice result from the EHT, which imaged the black hole shadow of M87 at 230 gigahertz, also in polarization using an array of just 8 stations. But we really see this as just the first step in black hole imaging. And we are working on plans to expand the EHT. And the first step is to add some new stations. And you can see on the left in yellow some stations that are planned to be added. And in fact, the 3 northern ones have already participated in the 2021 observations. And we see a GRMHT model here, and we then simulated observations with the 2017 and this extended array. And we see that when we reconstruct an image, we indeed see an improvement. With the additional stations, we get a sharper image of the shadow and start already, we start to see this extended jet feature. And then in this UV plot here, you can see that we get a lot of extra coverage with this new station. So in black is the 2017 coverage, and all the colored ones are the new baselines. And we see that some gaps here are filled in, giving us higher image fidelity and dynamic range. And we also get some longer baselines, for example, these ones to Greenland, so that our resolution is also increased. And we can go further than that. So there are now plans for building a next generation EHT. And this is an example array where 10 additional stations in red are added to the 2021 array. And with such a good coverage, you get a lot of UV coverage as shown in this animation here in a very short amount of time. And that means that you can track the dynamics of sources that vary on short timescales, such as Sagittarius A star, which varies on a timescale of minutes. And you can here see an example simulated reconstruction from a searing hotspot around the black hole, which with this coverage can be tracked very well. And for M87, where the variation occurs on much longer timescales, you can do multi-epoch observations with this array, and in this case also combining 230 and 345 gigahertz, and then see this dynamics of the jet, and you can also see these very low surface brightness features, and connect that to what happens really in the inner regions near the shadow. But then on even longer timescales, if you want to improve further than this, then you have to go to space. So the concept that we've been looking at is the Event Horizon Imager concept. And this is an idea that we've developed in collaboration with people at ESA. And the baseline concept which is 2 or 3 satellites in circular medium Earth orbits, the radius of about 14,000 kilometers. And then you can observe at very high frequencies that are not easily accessible from Earth due to corruptions by the atmosphere. And so we have been looking at frequencies up to 690 gigahertz. The idea is that these satellites will exchange the data and correlate on the fly, and then send the correlated data down to Earth for further processing. And to do this, you need to know the positions of the satellites, the orbits of the satellites quite accurately, which can be done with centimeter precision using GNSS satellites, which orbit further out. And then the data are shared over this intersatellite laser link, and that can also be used for distance measurements to the level of possibly tens of micrometers, and also for sharing the local oscillator, the clock signals between the satellites. And with that, you can make potentially a very phase stable interferometer, so almost like a connected interferometer in space. So there's a lot of technical research and development going on to see if this is indeed actually feasible. And the hope is that in the end, this may be suitable for something like a medium class ESA mission. So this is an example of a technical study that has been recently published. So you can find this on arXiv. This was led by Vladimir Kudryashov. And this is showing, this is a lab test of this concept where the clock signals are shared between the satellites. In this case, over an optic fiber of 5 kilometers. And the signals of the satellites 1 and the satellite 2, which has been going from this through this optical fiber, are then mixed. And because this goes in both ways, and these signals are traversing the same path here, you end up with 2 clock signals that are basically the same. And because of that, you can really integrate for a much longer time. And that is shown on the plots on the right, where on the top plot, we see the Allen deviation, which is a measure for the phase stability as a function of the averaging time. And when this line is crossed here, in this case for a frequency of 557 gigahertz, you basically end up with just phase noise for longer integration times than 10 to 40 seconds for these existing measures. However, this lab test has shown that if you employ this clock sharing scheme, then you can basically integrate for however long you want. This is well below the margins that are required for coherent integration. So this is a very encouraging first result, and there are plans to do this also at the IRAN telescopes to test this at an actual telescope site. But back to this event horizon imager concept. So it will have these satellites orbiting with a slightly different radius, which means that they will slowly drift apart as they orbit, and the baseline between them changes orientation and slowly grows. And then in the UV plane, you get this very nice spiral-shaped coverage where you basically sample all the Fourier components of the source up to a resolution of about 4 microarc seconds in this case. And this is very suitable for high fidelity and high resolution imaging. And you can see here again the same simulation, and now also simulated with this EHI concept, where you can really see an order of magnitude improvement and really see a very sharp image here of the black hole shadow, and also some of the details of the GRMHD simulation that was put in. We also did some detailed simulations of Sagittarius A star. And so here you see the GRMHD models that we use for that, which are at different inclinations, having a disk and jet emission. And we see here comparing the scattered and unscattered, that the interstellar scattering blurs the image, And this effect is much larger at 230 gigahertz, which the EST observes than at 690 gigahertz. So this is another reason to go to these very high frequencies, because then you're basically not bothered by the scattering anymore. And you see that also the emission is much more dominated by the emission close to the black hole shadow, allowing to image that more sharply. So this is now showing the signal to noise ratio in the UV plane on the spiral, which has been gridded here into grid cells. And there we see that if we take sort of conservative parameters for the noise, so this is based on a dish diameter of 4 meters, we see that we need to integrate for quite a while to get a signal on also on these very long baselines. So this would indeed require this long-term phase stability. So this is something to a motivation for really studying that further. But assuming that is possible, here are some reconstructions for these different models that I showed previously. On the top row, for just 1 day of observations with EHT, 2017 coverage as a reference. And then here in the middle row for the EHI at 230 gigahertz, and on the bottom row at 690 gigahertz. And indeed here you see we get these very sharp images of the black hole shadow. This is all assuming a static source model, but of course we know that Sagittarius A star is variable on short time scales. But if we believe these DRMST simulations, there will always be this lensed photon ring, this black hole shadow feature that is stable across all the time frames, because this is basically an effect from general relativity and not from the details of the plasma emission. So we've simulated also observations with a varying source like this, and then we see that after 1 month it still looks a bit noisy, although you can already see this shadow feature quite well. And then with more integrations, you get this very sharp image of the black hole shadow, despite the variability that is going on. For M87, the situation is quite different because it's variable on much longer time scales. And that means that with this EHI concept, it may be possible to image the dynamics of M87. And you can play with the separation between the satellite orbits because this determines the time it takes to completely fill this spiral up to from the shortest to the longest baselines. And here you see some simulations done by master student Anastasia Slentsova. We see here the coverage that you get within 1 gravitational time scale for a few snapshots on the horizontal axis at different orbit separations. So at small separations, we see that you basically get just concentric circles because the satellites don't drift apart very far within 1 gravitational time scale. But then when we increase the separation, we see that we get a larger part of the UV plane that is sampled within the gravitational time scales, but it is sharp. It is sampled less densely. And from these simulations that Anastasia did, it seems like an orbit separation of about 400 kilometers does well in reconstructing the dynamics of M87 with this concept. So here on the top row, you can see again a DRMST model and images reconstructed after averaging for 37 days at 230 gigahertz using 4-meter dishes. You can see you can already start reconstructing the dynamics of the source quite well. And then she looked also at the sort of EHI plus concept. What if we could actually launch 15-meter dishes? And then you see what you get back from the simulations is really just the GRMST model here that was put in. But of course, launching 15-meter dishes that can observe at this high frequency will make the mission far more difficult and expensive. So it will. It remains to be seen if that is worth it. So we also did some, apart from the imaging, quantified the results a bit more using parameter estimation. And for this, we used the same procedure as was used by the EHT collaboration, where we took a model library of GRMHD models of M87, which depends on a number of free parameters. So we have the black hole spin, the magnetic flux, the electron temperature distribution, and each of those simulations also has time variability. So they have 100 frames. And the approach that the EHT has taken is that each frame was rotated and scaled to optimally fit the EHT data. And then especially the scaling in size is interesting here, because that determines the angular size of the event horizon. And if you know the distance to the black hole, that gives you a mass measurement. So this is also how the EHT mass measurement was made. And we now do this with synthetic data using these different array concepts as input and see how things improve and behave. And we use the genetic algorithm GINA here for the optimization. We just take one model from this library, and you can see here different frames from that model. And you see there that they are quite different because of the orbits and the turbulence. But then, as shown on the bottom row, you can average these, and then in the end, you will get an image that is much more dominated by this photon ring and the black hole shadow feature. So we've simulated observations using either a single frame or multiple observations of different frames that are averaged, and then looked at the distribution that we get of the masses when fitting the different frames of this model to the synthetic data. And that is shown here. So on the left are the results for the ground-based array, where we see we get an improvement if we go from the 2017 array to the 2021 array, but then we get a much larger improvement using the same array, but observing for 10 days, looking at 10 different frames and averaging the observations so that we average out this variability, and we get an image that is more dominated by the photon ring, allowing us to make a better measurement of the mass. And then on the right, you can see the results for the EHI, the space Vibray concept, where we see that we get an additional improvement here of about about a factor 2. But this was assuming that the input model is actually known. But of course, we have this full GRMHD library, which gives a lot of additional uncertainty. And what the EHT has done is employed this method of average image scoring, where you test if the input data is consistent with being coming from a realization of the variability within a certain model. And if that is indeed the case, then that model is accepted, and otherwise it is rejected. And this model shows the fraction of accepted models of the GRMHD libraries with different spins for these different array concepts, using a model with spin 0.5 as the true input. And here we see that with the ground-based array, it's quite difficult to put strong constraints on the spin, although some values seem to be more favored than others. But then when we go to the space array, we see that this true input spin of 0.5 really gets clearly favored. And many of, for example, these retrograde models or the very high spin models that are in the library were ruled out in this example case. So here is another plot showing the width of the mass distributions for these all these different arrays. So in blue is the width of the fitting just the frames of the input model, and in orange is the fit to the full library after ruling out part of the library using this average image scoring. And we can see that there's still quite a gap between them. So this is telling us that it would be very fruitful to constrain these GRMHD parameters further, which can be done, for example, from multi-wavelength observations and polarization, which has not been taken into account here, and perhaps also a study of the variability. And we see in both of these cases, we get large jumps when we go from one frame to repeated observations of 10 frames. And in the best case here at 557 gigahertz, we could constrain the mass to about 0.5%. And this makes these tests of GR very interesting, because this is also about the precision that we know the mass of Sagittarius A star from the KEK and the gravity measurements. Yeah, so this is just a very high-level summary. So there's a lot of potential for the EHT images to improve with more stations added, and we can really make an order of magnitude improvement with space filled AI, of which the event horizon imager could be a very interesting concept. So that's it. Thanks.
Great, Frick. Thank you very much. A very good summary of this project, and we even have time to discuss it, to criticize it, or to say how wonderful it is, or ask questions. Colleagues, please go on. I'll give you 5 seconds to click the hand button or to just speak up. Okay, I cannot believe I have right now the chance to ask my question first. So the you know that one of the sort of worries which we have discussed for already quite some time was the ability or the absence of ability to fit fringes on the ground. So did you calculate how expensive would it be to allow for residual fringe fitting on the ground?
So you mean with that just transporting the raw data up to the ground?
It's okay. The best is if you can transport the raw data to the ground, but I mean, you want to stack the data in space, and stacking is the main worry, at least for me. So could you consider, so if you consider to try to improve your phase situation on the ground with, having the resources which will be available, the computing resource which will be available at that time on the ground. So is it completely impossible to send them, a much wider sort of flow of the data to the ground and solve this, and at least partly solve this problem on the ground, or you have to be, truly phase stable in space, and that's, if you cannot provide the specs, then the project is actually over.
Yeah, so I personally haven't looked at this in much detail, but yeah, it might be difficult to really do that for the full duration of the mission, because this is integrated for multiple months. It would need a very high bandwidth link to the ground for a long time. But I could imagine that one of the operating modes of the system could be that for part of the time it operates as a space interferometer, and then when highly sensitive ground stations such as ALMA are available, you could also do space ground observations and then send the data to the ground for a shorter amount of time. And then you can make use of this this high sensitivity there. And otherwise, yeah, it would either be needed to launch much larger dishes, or indeed to have this long phase stability. And then another option is to launch 3 satellites where you can use a closure phase, which further which puts less severe constraints on the phase stability that is necessary.
You did mention 3 satellites, right? So I mean, yes, it's so Andrei, you wanted to add something. You unmuted yourself.
Yes, I'm in the train. I'm not sure if you can hear me well.
Yeah, we can hear you.
Yes, but I'm in the train. I'm not sure you can hear. Good. I think 3 satellites is the absolute minimum that you really need for this kind of experiment if you want to have any chance of success. This should be considered a minimum constellation for that. But it of course puts lots of additional constraints on all your phase locking and everything, because you deal with 3 baselines at a time, and you have to be all phase locked essentially on 3 different baselines. That's not going to be the easiest task. If it flies off, it'll be very wonderful.
Thank you, Andrei. Actually, I do share this view that the 3 satellites is the minimum, because it will change the performance of the system and overall chances for success drastically. Talking about, my question about dumping raw data, or I don't know, data which are correlated with in a very wide range to the ground or something like that, was also related to the fact, all right, you launch the satellites and you don't see the signal. What would you do? You apparently observe, not your target, but you observe a calibrator or a source on the sky like 3C279, which you expect, okay, one of the brightest you expect to be at millimeter, sub-millimeter wavelengths. And then if you don't see fringes from it, then you want to dump the data to the ground, right? And to do all sorts of tricks with it, including correlation, which allows very wide fringe search, right? And then on the ground, finding the fringe and then helping your space to fine tune, right, the phase in such a case that then after this first phase, testing phase of your interferometer is over, you already fine-tuned its parameters so that then later you have high chances to get the actual signal. That, I mean, not using this mode for the whole mission, but at least for the testing phase, right? So that would possibly be an important option for the mission.
Yeah, I agree. It would certainly make sense to add that option. Yeah, of course, we still need to investigate how much more complicated and expensive this would make the mission. But yes, for the reasons you mentioned, I think it makes it the risk of failure seems to make it much lower.
Okay.
So I agree that it's something to definitely look at. Yeah.
Thank you, Freak. Colleagues, any more questions or comments? We have time for one more, or not anymore. So if you have any more questions or comments, please use the Zoom chat and we go on. Thank you. And the next speaker is, right. So we have Zachary with gravitational lensing in simulated and observed images of black holes. And I will give you a warning in 15 minutes.
Great. Can everyone see in here?
We can see your slides. We can see you and hear you fine.
Perfect. All right. So thanks so much. So my name is Zach Ellis. I'm a student at Harvard. And today I'll be talking about gravitational lensing in simulated and observed images of black holes. So I'd like to start out by talking about very high resolution images of black holes and the small scale features that we can identify in these images. So if we take a high resolution large field of view simulation like the one shown here, we can identify some of these features right off the bat. Things like the jet launching structures that show up in the jet base and give rise to these fine features out here. And if we zoom in on the image and focus on an even narrower field of view, we start to see even more features emerge. So we can see things like the turbulence in the accretion flow that's driven by the magnetorotational instability and causes these wispy arms in the plasma to form out here. And we can see relativistic effects as well, such as light bending, which cause the photon ring to form at the center of the image here. Now, we've seen a couple talks, and Mina and Alex did a really great job explaining the photon ring science. So I'll just take 30 seconds to recap the main points that I'll be discussing. But we get a photon ring because each emitter surrounding the black hole emits an infinite sequence of images. And each of these images can be indexed by an integer n called the subring index, which counts the number of half orbits that each geodesic completes in connecting the emitter to the observer. And so this naturally breaks down the black hole image into a series of successive subimages, each of which is indexed by these numbers n. And so the total image can be thought of as a sum of n equals 0 plus n equals 1 plus n equals 2. And this is the same figure that Mina showed. And it's important to note that because each subring has constant peak brightness, even though it has constant peak brightness, the strong lensing will cause each subring to be demagnified, and therefore each subring will be suppressed in flux. And one can show, as Mina described, that this subring is exponential, which is to say that the width of the nth subring goes like e to the minus gamma n, where gamma is a so-called Lyapunov exponent that depends on the spin, inclination, and conserved quantities of the particular geodesic that we're looking at. So with this idea now of where the photon ring comes from, we want to be able to resolve it and see it. Of course, our ultimate goal is to do this in real interferometric data. And as we've seen throughout this conference, and as I'll show, a really great way to be able to do that will ultimately be with space VLBI. But before space VLBI, we want to be able to resolve the photon ring in simulations as well, which presents a challenge in and of itself. So when I talk about simulations, I'm specifically referring to simulated images of black holes generated via general relativistic ray tracing, which is a technique where a hypothetical camera is set up far away from the black hole. The geodesics are then traced through the space-time, and radiative transfer is then integrated along them to determine what this image ultimately looks like. And this technique works really well, but it's still hard to resolve the higher order photon subrings because they are exponentially suppressed in width, and therefore we need to trace many, many rays to be able to resolve the subring substructure, which ultimately is a very computationally expensive procedure. To put this in perspective, we can look at a sample image from the Event Horizon Telescope image library. So the EHT maintains a library of images, of ray traced images, and in particular, this is maintained by the University of Illinois. And one such sample image is shown here from the EHT paper 5. And we can see that this sample image only resolves the n equals 1 subring. That's this thin ring of light here. This is n equals 1. If we wanted to resolve n equals 2, we would have to kick up the resolution in this image by a factor of over 20, which would be incredibly computationally expensive, and it is not particularly practical using the same ray tracing techniques. But that's okay, because there is a practical solution to this problem. What we can do instead is to alter our sampling strategy so that while we're ray tracing, we sample rays more finely near sharp features in the image and more sparsely everywhere else. Since if we want to see the photon ring more clearly, we don't need to uniformly increase the resolution everywhere. We just need to do that in the very thin vicinity around the ring itself. And this motivates the idea of adaptive ray tracing. So over the past year, I've been working on an adaptive ray tracing algorithm to see the photon ring more clearly, and it does just this. It samples more finely in areas of interest on the image, such as the photon ring and turbulent accretion flow, while sampling more sparsely everywhere else. I worked with collaborators including Ben Prather, Daniel Palumbo, Michael Johnson, George Wang, and Boris Georgiev. And this was recently published in a paper in AppJ. And other examples of adaptive refinement have also been used in semi-analytic models in the past, such as those described by the Themis package in Avery Broderick's work. For our purposes, we were primarily focused on using adaptive ray tracing to see small-scale GRMHD features and see the photon ring in GRMHD. And to that end, we took the pre-existing ray tracing code IPOL and we modified it to include this adaptive ray tracing component. We then ray traced the images from the general relativistic magnetohydrodynamics, or GRMHD, simulations produced by the University of Illinois. And in doing so, we had 3 key goals in mind. So first, we wanted to develop refinement strategies to isolate regions of interest on the image. And we wanted to do this in a way that was not eye-pole specific, but could rather be applied to any number of ray tracing codes. Second, we wanted to probe the structure of the n=2 and n=3 subrings, since as we saw, the current EHT image library only gets n=1. And finally, we wanted to develop insights into the best VLBI techniques to image small-scale features and try to take away conclusions from these simulations to better improve our understanding of data in the future. So the algorithm works in the following way to generate these high-resolution images. To start, we start by ray tracing. If we want to ray trace a high-resolution image, we start by ray tracing it at a low resolution on a uniform grid. So we might start, for example, by ray tracing 33 by 33 pixels, 33 by 33 rays on this uniform grid, which gives a very blurry looking picture of M87 here. But even though it's blurry, that's okay, because what we do in the next step is the most important part. We go back and we specifically implement a recursive refinement procedure, where first we double the resolution at each step. So this 33 by 33 will get kicked up by a factor of 2. And then at the new resolution, we concentrate rays in sharp regions of the image while interpolating everywhere else. To determine where we ray trace versus interpolate, what we do is we compare the expected interpolation error to a specified pair of relative and absolute tolerances. If the tolerances are exceeded, then we ray trace, but if the tolerances are met, then we can comfortably interpolate without worrying about losing accuracy. And we quantify the amount of interpolation at each stage of the process with an interpolation fraction. At this point, it's 0 because we've ray traced every single pixel on the image, but that changes as the recursive refinement procedure kicks in. So that 33 by 33 becomes 65 by 65, where now we're concentrating rays much more finely towards the photon ring and accretion flow. And the interpolation fraction is jumping as we interpolate pixels on the outskirts of the image. The process then repeats. Again, interpolation fraction is climbing, effective resolution is climbing as well, until finally we reach our final desired resolution, in this case 257 by 257 rays, while we're interpolating nearly 80% of the image. And we're able to do this in a way that is both fast and accurate. If we look at extremely high resolution images, well beyond this 257 by 257, we find that we're actually able to generate images with over 12 times fewer rays, and with a normalized flux and mean squared error of less than 10 to the -3 when comparing adaptively ray traced images to their traditionally ray traced counterparts. So we can do this very quickly and very effectively without sacrificing accuracy. And so now that we have this algorithm, we're able to use it on GRMHD to specifically look at the photon ring. So as we saw earlier, the black hole image naturally decomposes into a sum of individual subrings. And thanks to a module written by George Wang, we can decompose these individual images, these GRMHD images, into the photon subrings. And we can do this at unprecedented resolutions thanks to adaptive ray tracing, because we can concentrate the rays on the photon ring itself. So we used adaptive ray tracing to generate images at 32,000 by 32,000 pixels over a 22M field of view, which gave us incredibly high resolution probes of the subring structure, as we can see here. So we have n=0, n=1, n=2, and now we can even see n=3 in these images. And we can see that they are not just thin rings on the sky, but rather do display important substructure that can be probed. And when we stack these subimages back together, we do in fact reproduce the original image that we started with. So now we can see these subrings very clearly in the GRMHD. And from here, what we like to do is to be able to apply that to interferometry, which means that we have to take Fourier transforms and look at the visibility spectra of these images. Now, as Mina explained, we expect the visibility signature of a photon subring to have some periodic oscillating decay. And in particular, it should look like a Bessel function of the first kind. So that said, if we take a look at an adaptively ray traced high resolution image and we compute its visibility amplitudes along a horizontal slice, we find that this does not look like a Bessel function. It doesn't have this nice periodicity. Instead, it shows a very complicated stochastic structure in the visibility amplitudes of this image. To understand where this complicated noise is coming from, it's useful to actually decompose the Fourier transform. So in this particular plot, we're showing, again, just the visibility amplitudes, but specifically for each individual subimage, with the red showing the visibility amplitudes of the total image, the green showing the visibility amplitudes of the n=0 image, and the blue showing the visibility amplitudes of the n=1 image. And now we can see a bit more clearly what's going on and what's introducing this noise. If we zoom in on this one region of the plot, we see that the blue curve, the n=1, does look like a Bessel function. It has that nice damped oscillation. It's the green curve, the n=0, that gets in the way by introducing this high-powered noise. Now, that high-powered noise specifically arises due to the existence of turbulence in the accretion flow. So because we have these MHD turbulent sources, this introduces lots of fine-scale structure, which corrupts the visibility spectrum of the photon ring on this relevant range of baselines. But that's okay. What we can do is we can time average the simulations to very easily mitigate the effects of this turbulence. Since, as Frake showed us, if we average over many images, we expect the turbulence to get washed out while the photon ring signature is there to stay. The turbulence lives on short timescales, but the photon ring is a feature of strong gravity, so it's not going anywhere. And this becomes uniquely possible with adaptive ray tracing because now we have the ability to ray trace large quantities of simulations that we can time average over, but each of these individual images is now capable of having a high enough effective resolution to see all of this, or to see many subrings. And so in particular, if we take the single snapshot visibility spectrum, what we did is we used adaptive ray tracing to average over a time scale of 500 M, which for M87 is about 5.5 months. And in doing so, we then took Fourier amplitudes, excuse me, of the time averaged image, and we saw a much different picture. Zooming in on, again, this relevant range of baselines, we see that the blue curve, the n=1, does look the same, still looks like a Bessel function, but it's the green curve, the n=0, that's been dramatically suppressed. And again, that's because we're specifically washing out the turbulence as we time average over the simulation, allowing the photon ring signature to rise up and be seen more clearly in the total spectrum of the image. This is important for a number of reasons, but in particular, it tells us about the timescales over which accretion turbulence varies in these images, and that in turn can inform us about the timescales necessary to observe sources within a interferometry. So in particular, we can apply the things we've seen to VLBI. It turns out that the relevant baselines that we saw the photon ring signature living at are most readily probed with space interferometry. So we can show the exact same plot that I showed on the previous slide, the subring decomposed visibility amplitudes, and we can look at what kind of array configurations would be able to probe this parts of visibility space. So a ground array can create baselines that are only so large. And so as order of magnitude estimates, we expect ground-based arrays to be able to take us about this far in visibility space, which is not far enough to be able to see this periodic ringing of the photon ring. However, if we were to use a geosynchronous orbiter and put a station in a geosynchronous orbit that would form a baseline with the ground station, then, again, order of magnitude estimates on the distance of these projected baselines, we would actually be able to probe the relevant portion of the visibility spectrum to see the photon ring with sufficient averaging. And this actually becomes even better if we switch to 345 gigahertz. So working with Alex Raymond, who's also at Harvard SAO, we ray traced the same simulation adaptively at 345 gigahertz and found that this sees the photon ring even better. And this is because with a higher observing frequency, two stations separated by the same physical projected distance will extend out farther in their U and V coordinates. So we can extend out, so by upgrading to 345 gigahertz, we can get farther out in the visibility spectrum and therefore see the photon ring a bit more clearly. Now, it's from here, it's worth talking a little bit more about observing frequency because not only does great. So I want to talk a little bit more about observing frequency because not only does observing frequency extend us farther out into visibility space, but a higher observing frequency can actually make the photon ring relatively brighter relative to the n=0 direct image. We can see this clearly in GRMHD simulations. So for example, if we look at a very low frequency image of M87 shown here, and compare it to the traditional 230 gigahertz image shown here, when we plot these two images on the same scale, we see that the photon ring is comparatively much brighter in the 230 gigahertz image. And so it dominates a larger portion of the relative flux in the image. And this is because of optical depth. Higher observing frequencies correspond to lower synchrotron opacities through the medium, which in turn affects the photon ring, because if we have a very high opacity, then photons will be attenuated before they can complete many orbits. And so we can't see subrings with large n. Whereas with low opacity, if the medium is optically thin, then rays can make many revolutions around the black hole without being attenuated. And so we'll be able to see higher order subrings. And this is something that we've used adaptive ray tracing to help quantify. So earlier with Maciek-Wielgus, we used adaptive ray tracing to extract the frequency dependence of photon ring flux by ray tracing through these simulations as a function of observing frequency. And with this particular simulation, we found that the trend extends past 230 gigahertz as well. So in this plot, we're showing observing frequency nu on the x-axis, and on the y-axis, we're showing the ratio of flux contained in the n=1 subring. And we find that it is increasing strictly as a function of observing frequency. So while at 230 gigahertz, we might only get 10 to 15% of the photon ring flux contained, or 10% of the image flux contained in the ring, by the time we get to a terahertz, we can see as much as 25% of the image flux contained in the ring. And again, this is due to optical depth considerations, since at higher frequencies, the medium becomes optically thin. So in summary, we now have the tools to understand the relativistic signatures that show up at extremely high resolutions and allow us to produce simulated images like these. And we can use these simulations to help inform us about how to optimize space missions and future VLBI efforts. So we've used simulations to investigate three main quantities in particular, first being the relevant timescales for averaging, so that the visibility signature of the photon ring can be drawn out. The second being baseline length considerations and how changing from a ground array to say an orbiter, or to say a station in geosynchronous orbit would help us. And the third being the dual role of frequency, in that increasing the observing frequency both allows us to extend out farther in visibility space, but also strengthens the relative flux of the photon ring. In the future, there are a number of directions we can go. We'll certainly continue to do everything we've already been doing, continue to probe the photon ring substructure in these simulations, and letting that guide us our instrumentation and future VLBI efforts. And on the specific simulation front, we might consider ways to improve the resolution of the GRMHD simulation itself, the actual number of GRMHD cells in the simulation, since this is a limiting factor in our simulations. And we could also extend our adaptive code to look more closely at the jets and those small scale features that live on wider fields of view. Just super quickly wanted to mention that the adaptive code that I've used is publicly available at this link. You can also feel free to email me. And I'd like to extend a big thank you to everyone at Harvard SAO and everyone who's helped out with these various projects, and of course the organizers of the Marcel Grossman meeting. So thank you so much, and I'd be happy to take any questions.
Thank you very much for the great talk, Zachary. Thank you, Alex. Oh my God. Okay, three questions. And we run out of time, but I will give time to all three questions. And sorry that I didn't manage to stay in time. Very well, Alex, please go on.
Yes, thanks for the great talk, Zach. Can you maybe at some later time show us cross sections of the photon ring image at a higher frequency? Because in the image you showed on the previous slide, it looks extremely bright. And we expect that the brightness in the ring should be about twice the brightness of the direct emission, because the n=1 ring contains light rays that cross an extra time, so they should pick up twice the intensity. But in that image, it looks like it's much more than twice the intensity, which is a little bit puzzling. But maybe it's a trick of the eye.
Yeah, that's, I think, yeah, we should definitely look at cross sections to see what that looks like. This may be an artifact of the plotting scale that's being used here, just because I wanted to plot on the same scale for 86 versus 230. But at the end of the day, it is just dimmer at 86, so the plotting scales don't naturally align that well. But I wouldn't be surprised if this is actually a factor of 2.
Okay, because this looks really too good to be true, unfortunately.
Thank you. Short questions, short answers, Andrew.
Yeah, thanks for the great talk. Can you go back to your slide 12? I just have a question on there.
Slide 12, yeah.
Yeah, I think I just missed this in your talk, but it basically is just like, how are you identifying the different subrings when you do these great decompositions? Is that purely spatial in location, or is it based on the number of turning points that the geodesics execute?
It's the latter, yeah. So it's counting turning points in Boyer-Lindquist theta, yeah.
Yeah. I guess if just the point of the question is just that the image to me here looks sort of like it's becoming optically thick. So at some point, I think you would not see any subrings, right? But with that kind of strategy, you might still put power there, even if they're indistinguishable. But I think this is kind of.
Yeah, that's a very fair point. And so when you do switch to optically thick, what ends up happening with this particular decomposition scheme is you just get super small intensities along the rays. So you're right, it does put some power there, but it's very, very negligible in the optically thick limit.
Wouldn't you have, well, I think we should maybe discuss this.
Sorry, could you please follow up on that in the chat, Aditya, and we go to the next talk.
Yeah, just a small question in the same slide. How exactly did you get the Bessel function? I mean, did you solve an equation? How did you get this? And is it an astrophysical effect or a GR effect, this Bessel function behavior?
Oh, you're talking, okay, right. So so the specific Bessel function, the Fourier transform of a delta ring of just an infinitely thin circular ring on the sky is just J0. It's a Bessel function of the first kind. For non-uniform rings, this gets modified. And then when you add thickness, this gets modified as well. But as Mina alluded to in her talk, when you're in the portion of visibility space that can't yet resolve the thickness of the ring, it's as if it were a delta ring. So you can treat it as a Bessel function. As for whether or not this depends on the astrophysics, it will, in the sense that I think this might have been discussed on Tuesday, but suppose you were to have, say, spherically symmetric accretion, then your geodesic wouldn't execute discretized passes through the medium, but would rather just sort of continuously pass through the medium, so you wouldn't get individual subrings that separate out from each other. So I guess that's one example of how the astrophysics could affect this, yeah.
Thank you. Okay, we move to the last talk of the meeting today. So it is Jonathan talking about the coolest radio astronomy from space, the fundamental cosmology from the cosmic dark ages, the case for a very low frequency lunar radio array.
Okay, great. Thanks. My screen coming through okay?
Yep.
All right, great. Thanks to everybody for sticking around. This is going to be a bit of a change of pace from what we've been hearing this session. So we're definitely talking about radio astronomy from space, but less so black holes. Recognizing that a lot of folks here probably aren't cosmologists, so I'll keep this at a relatively high level and really in the outline spend a lot of my time going over the cosmological case for making these kinds of measurements, in particular, talking about the cosmic microwave background and its limitations, and suggesting this 21 centimeter signal from the cosmic dark ages, and I'll explain what those terms mean, but suggesting that as kind of a new frontier for cosmology, moving beyond the cosmic microwave background, and then describing the lunar array that could potentially make these measurements. So let's start by talking about the CMB, what it's done for cosmology, and what it can't do. So I would argue the cosmic microwave background is the most important source of information about cosmology that we have. It's a snapshot of the universe 380,000 years after the Big Bang. And what we see in this map from Planck are very small fluctuations in the temperature of photons. I say they're very small fluctuations. The map is highlighting the contrast, but these are 1 part in 10 to the 5 around the mean value. And so the universe 380,000 years after the Big Bang is incredibly uniform. But these tiny, tiny fluctuations in the photon temperature are tracing tiny, tiny fluctuations in the density of the universe. That regions that are blue are ever slightly, 1 part in 10 to the 5-ish, ever slightly more overdense than regions that are red. And given 13.8 billion years, gravitational collapse takes those overdense regions, grabs a little bit more material, it grows and grows and grows, and that is the source of all structure we have in the universe. All clusters of galaxies, the cosmic web, all of it grew out of these very small density fluctuations that are traced by the cosmic microwave background. But what in particular makes it so valuable a cosmological probe is that the power spectrum of those density fluctuations is analytically calculable and predictable. So if you have a model of inflation, which is currently our best model for why there are any fluctuations in the cosmic microwave background to begin with, you can predict what the power spectrum of the CMB is. So for power spectrum, recall, is a metric of sort of how much intensity there is in a fluctuation as a function of angular scale. And so in red, you see measurements from the Planck satellite. They've done that spherical harmonic decomposition of that CMB map and return this data. The green line is a best fit that contains just 6 parameters to fit that model. They're key cosmological parameters, the amount of baryons in the universe, the amount of dark matter, the age of the universe, 2 parameters related back to this inflationary epoch that's at the amplitude and the spectral index, so sort of a tilt of this power spectrum. And number 6 is actually just a nuisance parameter in a sense that the CMB photons do interact between 380,000 years after the Big Bang and when they reach our telescope. And so we need to calculate the optical depth between us and the CMB to a photon. But again, the key here is that this prediction can be made with such high accuracy with such few parameters because the physics is very well understood. The physics of recombination when the CMB forms as the universe is becoming neutral, and the physics of sound waves traveling in that primordial plasma. It's extremely well understood. It's linear physics, and it lets you map with, again, just a few numbers, get this green curve. And so you can download, there's actually a Java applet for CAM on the Cosmic Microwave Background website. You can go, you can put in your 6 parameters, and in a matter of seconds, it spits out the green curve. It's not a simple calculation, but a semester course in graduate school, and you'll know everything that goes into this calculation. And I should say you can extend the model beyond these 6 parameters. There's lots of other physics you can put in. Is the universe have global spatial curvature? Is there some type of extra neutrino species? Whatever you like. But right now, just these 6 numbers gives us the best fit to the data. There's no compelling evidence that we need a 7th or 8th or 9th parameter. But the CMB does have its limitations. So the most obvious one you can see in this plot is kind of this region here on very large angular scales. The error bars on the data get big, and the prediction has this green shaded region around it, a confidence interval due to cosmic variance. So this is sample variance on the cosmic scale. You can think of it as this mode corresponds to a 90-degree patch of sky. Well, how many 90-degree patches of sky do I have on the entire sky? Not many. And so you just statistically can't get great measurements of these very large scale angular modes. And that potentially is a problem because, as you'll notice, some of these modes, this one here, this very largest scale, are inconsistent with the confidence interval at marginal significance, 2.5 sigma. It was not the kind of thing that would keep you up at night, but we can't get better data out of the CMB. You can't beat cosmic variance because we only have one universe. There are only so many of these scales on the sky. And so these kind of large scale anomalies, if they're real, are stuck at this level of significance. We also have issues on the small scales. So right, going toward these very small angular scales, you can see the power in the CMB is dropping. If there's a lot of power at this 1 degree peak, these next 2 peaks are pretty big, and then it's really dropping. And you can see this on a modified plot. This is the same data plotted on a logarithmic Y scale. Planck data is in blue. You can see it's petering out. And around here, multipole moment of 2500. Other CMB experiments from the ground can go to smaller scales, but this power is just dropping like a rock as you go to small scales. And that's due to photon diffusion, also known as silk damping, the fact that the CMB is tracing perturbations in the photons themselves. And so if you go and you try and cram a bunch of photons into a really small region, there's radiation pressure. They push back and they erase that perturbation. And so that damping erases small scale power in the CMB. That's unfortunate because there's tons of interesting physics you can get if you can probe the small scales of the density power spectrum, the running of the spectral index, spatial curvature, neutrino masses, the nature of dark matter, lots and lots of information in those small scale modes, but they're not in the CMB. And so again, I want to emphasize that this damping effect is specific to the cosmic microwave background. It's because it's perturbations in the photons that they diffuse away. It's not, that there is no small scale power in the universe. And lastly, the CMB, this is kind of related to the last 2 points, but we're just limited in the number of modes we can get. It is a surface. And so you can only fit in so many modes of specific angular scales on a surface. And when you take into account that small scales have this information being wiped away, there's just a fundamental limit to the amount of information in the CMB. And that's a limitation to making measurements of non-Gaussianity, asking whether these perturbations are completely Gaussian distributed. Within our statistical confidence, they are, but if they're not, that would be evidence for a more interesting model of inflation. And fundamentally, the answer is if you want to get more modes, we don't want to measure a surface. We want to measure a volume, where you have modes not just on the plane of the sky, but along the line of sight, and then every direction that's a combination of those 2 directions. And so one way to go about that is to do a galaxy survey. So this is a footprint of all the galaxies observed by the Sloan Digital Sky Surveys over the years. And they spectroscopically get the redshift of every galaxy, put it in position space, and map out the density field using galaxies, using quasars in 3D. So that's one way of going after a volume. You can see here that they're only getting out to a fraction of the observable universe, right? The CMB is out here, whereas all these different galaxy surveys over the years only get out halfway, and that's a potential issue. But the bigger issue with doing a galaxy survey is that small scale information, like I said, is absent from the CMB. It's not absent in a galaxy survey, but it's much, much harder to interpret. And that's because galaxy formation is complicated, right? Once a perturbation, a density perturbation grows big enough, the equations of its growth become nonlinear. You have to deal with the fact that it becomes dense enough to form stars, stars form galaxies, galaxies merge. All the things that are happening on these really small scales are no longer calculable, with a Java applet on a web page to get arbitrary levels of precision in your power spectrum. You need to know how structure formation is working at extremely high levels of precision to interpret the small scale information that comes out of galaxy surveys. And that's just not possible at the moment. So given those limitations, I want to propose an alternative or present an alternative, and that is this dark ages 21 centimeter signal as kind of a next step forward for cosmology. So here's a map of the timeline of the universe. The dark ages is this period between the formation of the cosmic microwave background and the formation of the first stars. And so it's a period when the universe is really, really boring. It consists of dark matter, hydrogen, and helium, and trace amounts of lithium, and it's not doing much. Those density perturbations are there. They are slowly growing, slowly becoming dense enough to form the first stars, but they haven't become very large yet. So it's a fantastic probe of the density field of the universe that we want to use to test our cosmological models. The problem is there are no sources of electromagnetic radiation. It's the dark ages. So the CMB photons are present, but they're not interacting with the matter anymore. There are no stars. There's no other light with which to probe the dark ages, with the exception of the 21 centimeter hyperfine signal from neutral hydrogen. Right, so neutral hydrogen, as I said, is most of the baryonic matter in the universe at this time, 75% by mass, and it has this very fine or hyperfine spectral line in it. The difference between the state where the proton and the electron are aligned and anti-aligned is a very small energy difference, depending on what units you like to measure energy. It's micro electron volts, corresponds to 1420 megahertz in frequency, 21 centimeters in wavelength. If you like to think in an equivalent Boltzmann temperature, it's fractions of a Kelvin. And that last number is key because that means we have all this hydrogen sitting in the CMB. The CMB has formed, those photons are out and about in the universe, and that CMB is always hot enough to excite the hyperfine transition. The CMB is hotter than 0.068 Kelvin. And so that means this signal, the excited states get populated, and there is a signal to observe from neutral hydrogen. It also happens to be a spectral line, which for cosmology is very valuable because you can map the redshift of the line to the cosmological distance. And so making a spectral map of the 21 centimeter hyperfine signal during the dark ages solves a lot of these problems with cosmology, or with our current cosmological observables. So as I said, it probes a volume because we have that spectral dimension that maps to redshift, that maps to distance along the line of sight through cosmic history. That small scale structure damping, the silk damping, is not present because the hydrogen is free to collapse all the way down to the gene sling. There are no radiation pressure causing it to expand and erase small scale power. And so you can observe down to very, very small scales. Right, this plot here shows several alterations of the cosmological model and how they behave on very small scales. Or you may recall this the multipole moment L, the CMB was kind of losing information around 3,000, 4,000, and just can't tell the difference between these models. But with the 21 centimeter signal going down to much smaller L, you start getting all sorts of differences. And these various models correspond to whether there's massive neutrino dark matter or warm dark matter or a more complicated inflationary power spectrum. That information is there in the 21 centimeter signal, and it's not there in the CMB. Structure formation is also still in the linear regime. As I said, the perturbations have not gotten very large. And so you don't need to deal with the physics of star formation and galaxy formation and halo merging. It's still very straightforward to interpret this signal. So those small scale modes are interpretable. And all told, there's over 1 million more modes in the dark ages than there are in the CMB. So you don't even need to go down to these very, very small scales to start beating the CMB. As I said, CMB is kind of running out here. And even another order of magnitude starts letting you distinguish these models. So there's a tremendous amount of information in this signal that really exists in no other cosmological observable. So that's the excitement, right? That's this signal really could be revolutionary for cosmology. The hard part is going to be observing it. And so I will make the argument that the only way to do so is with a low frequency radio interferometer on the far side of the moon. And the rationale for that follows from a couple points. First, that dark ages 21 centimeter signal is very faint. A number to keep in mind is sort of a brightness temperature of a millikelvin. And so if you go and you do some sensitivity calculations, a kind of round number to keep in mind is if you want to get a millikelvin signal at these very low frequencies where your noise is dominated by the sky brightness temperature, you need about 5 square kilometers of collecting area, observing for about 5 straight years. Again, that's not the exact number, but that's kind of a nice round number. 5 square kilometers for 5 years to get down to a millikelvin. And I should say that that's a detection. Right? If you want precision cosmology, it's going to have to be bigger than that or longer than that. What makes it really hard is that all the other radio emission down at these very low frequencies is very bright. So here's a map of the sky from the long wavelength array at 74 megahertz. And you see a unit that you don't see a lot, kilokelvin. Right? The radio emission down at 74 megahertz is in the multiple kilokelvin. We're trying to pull out a 1 millikelvin signal. That is the biggest challenge for this experiment, the removal of astrophysical foregrounds. There's no way around it. You'll have to find a way to do it, but it's not easy. Also, at these very low frequencies or very long wavelengths, we're dealing with regimes where the Earth's atmosphere is no longer friendly to radio astronomy. So these are decametric wavelengths, greater than 10 meters. And you can see, on this figure, the radio typically is thought of as having a nice clean window through the Earth's atmosphere, but at these very low frequencies, greater than 10 meters, the ionosphere becomes opaque. Right, so all the talks previously in the session, we're talking about going to space for better angular resolution and to deal with the atmospheric issues up here. We're dealing down here with the ionosphere. And if you get into the nitty-gritty of it, the ionosphere is variable. Much quieter during nighttime. You can get to frequencies, maybe even as low as 10 megahertz during a couple nights a year, during solar minimum. So it's not so clear that absolutely never can you do radio astronomy at 10 megahertz from the ground. But if you go back to that 5 square kilometers for 5 years, the ionosphere clearly becomes an impossible obstacle, right? If we're going down from a year of observing time to 10, 20 nights a year of observing time, now we're talking about a 50-year experiment, not a 5-year experiment, and that's just not feasible. And it's also worth noting that RFI, radio frequency interference, at these very low frequencies is a huge problem. Lots and lots and lots of transmissions below 30 megahertz. So the place to do it is the far side of the moon. It's stable, right? You can put a low frequency radio telescope with a very large collecting area, and it will sit there patiently for as long as you need to take the data. But more importantly, there's no ionosphere, and it provides a shield from terrestrial interference, right? The moon itself is between you and the Earth, and so it blocks most of that interference. And so it is not an overreach to say this is simply the only place this experiment can be done. It's such a challenging experiment, but this is a requirement. We need to be in space on some sort of ground, shielded from interference. The far side of the moon is the place to do it. So to wrap up, I just want to highlight some of the technology development that's happening and needs to happen to make this anywhere close to possible. Well, you need to figure out how to build the array. thankfully, at decametric wavelengths, and what you think of as radio telescopes are a lot simpler than, right? So a dipole laying on the ground is a radio telescope at 30-meter wavelength. And so there's proposals to have a rover lay out these tethers with the dipoles embedded in them and have those make up your antenna elements. There's actually a very recently funded NASA advanced concepts proposal to look about maybe you could manufacture the radio antennas directly from the lunar regolith in situ. That's the far view concept. But getting 5 square kilometers of collecting area deployed on the moon will be a challenge. And so that's a technology that still needs to be addressed. Data rates are also an issue. Most people are thinking, a dedicated orbiting beacon to take data from the array when it's above the far side of the moon, send it back to the Earth when it's on the near side of the moon. But actually getting the data from an interferometer this big compressed to fit in that bandwidth is a challenge. Thankfully, the fringe rates on the far side of the moon are very, very low. So you can average for a lot of time, that helps. But getting the data back requires further investigation. And the last thing I want to say is we need more work on how to analyze the data from these experiments. And I could give an hour-long talk on this. I'm not, I promise. We're almost done. But data analysis is really hard. I haven't mentioned that a lot of experiments targeting the 21 centimeter signal from intermediate redshifts, redshift 10, where you can do these observations from the ground. These experiments have been operating for over a decade now. The names you may have heard are the MWA, LOFAR, PAPER, HERA. We've learned a tremendous amount from operating these experiments, but none of them have made a successful detection of the 21 centimeter signal. And the reason for that is that foreground mitigation, the challenge of picking out the faint signal from underneath the foregrounds, demands incredible calibration of your instrument. You need it modeled in real time per antenna with extreme spectral precision. And we don't have the techniques to do that. We've been building them and we've been getting better, but that problem is not solved. And so there's a lot of lessons to be learned. But ultimately, I would say the key takeaway is that we need to build an instrument with the data analysis in mind. They go hand in hand. The instrument design can make the experiment harder. You can't just fix it in data analysis. Rather, you need an instrument design that makes data analysis easier and then fix it in data analysis. And so, this last plot is just showing that the most popular technique on the ground sacrifices modes to the foreground. It's called foreground avoidance. And on the ground, we're losing about 80% of our modes to foregrounds and still making do with that. But out in space, we're losing 95% plus. And with that sensitivity challenge, it just isn't going to work. And so we really need to think about how to calibrate these instruments and how to deal with foregrounds before we build the experiment.
2 more minutes, Don.
Oh, so I'm at my conclusions. I really would argue that these dark ages 21 centimeter observations are a bold new future for cosmology. And one thing I want to stress is, even if cosmology is at its most boring, right? Even if dark matter is a WIMP and dark energy is a cosmological constant and inflation is a very, very vanilla model, the information that comes out of a 21 centimeter dark ages experiment will be transformative. Getting to those small scales is just an order of magnitude more precision. And of course, if any of those things turn out not to be true, if there are more interesting models of dark matter or dark energy or inflation, the information is there in this signal to constrain them. So it's a hard experiment, but it's the only way to do it. And I think, as we work towards getting that really large experiment on the moon, we're looking towards kind of pathfinders targeting other low frequency radio science, exoplanet magnetospheres, stellar weather, putting those on the moon and learning about 21 centimeter cosmology along the way. So this isn't an experiment that's happening next year, but the work to make it happen in the next couple decades needs to start now. that, I'll take any questions. Thank you.
Thank you very much, John. This is wonderful, wonderful concluding talk for the session. So there is a question from Michael, and we'll see if mine is similar to yours, Michael. So okay, go on.
Yeah, thanks, Jonathan. That was really nice. I was just curious if there was something already in the new instrument design for something like Farside that will make calibration easier, and if not, what sort of instrumental customization do you have in mind to sharpen the calibration?
So yeah, I think calibration for these experiments we've learned is not going to be solved with one thing. There's no magic breakthrough that just makes calibration work 3 orders of magnitude better. It's going to be a factor of 2 here, a factor of 3 here, and just getting it down and down and down. And one thing that is unique to the Farside design is the idea of using this orbiting satellite as a calibrator beacon, that having a known signal that makes the sky simple. It's always easiest when your sky is a single point source. Right? At these low radio frequencies, the sky is filled, and your fields of view are huge with these dipole antennas. And so you almost never have a single point source sky. And well, if you can make the sky a single point source, it's a lot easier to calibrate. One challenge is its spectral calibration. And so you need to know, not just have your beacon emit at one frequency, it needs to emit across the whole band and be well understood across the whole band. And people have tried this on the ground with drones. There's challenges to having your drone transmitter at the exact right angle to the antennas when it gets down in the far field, having it strong enough. And it's just hard to fly drones screaming radio signals at the national radio quiet zones of various countries. They tend to frown upon that. So we haven't had too much chance to investigate that technology. But I think having an external calibrator will be a real step forward.
So you're thinking it's mostly after the fact. It's not in the design of the antennas or something so much.
I mean, I think, no, absolutely, the antenna design has to be calibratable. Mm-hmm. And that requires simulation and balancing the trade-offs, particularly here between being deployable. Something like a dish might be more calibratable than a ribbon antenna like this, but that has to be balanced. But once it's up there and once it's built, I think you can't solve it all with hardware in this case. You can't solve it all with software either. You need the two to work in tandem.
Great, thanks.
Thank you. So no, my question is different and apparently provocative. So Jonathan, I am an NASA official, which tells you that it is a wonderful idea, but we will not give you money because SKA law will solve it all. What will you reply to a NASA official saying you this stupid thing?
So I think 21 centimeter cosmology means a lot of things because there's such a range of redshifts you can probe, right? You can probe from redshift 1 all the way up to redshift 200. And the same experiment can't do that, right? That's 800 megahertz to 10 megahertz. And building one antenna with a factor of 80 in bandwidth and keeping it spectrally smooth cannot be done. And so I think the first thing I would say is the SKA is not targeting this science. They're pushing up redshift 20, maybe the high 20s to go after the first stars. But this period that's really rich in cosmology is redshift 50 to 150, and that's not in the purview of any ground-based instrument. And I think the ionosphere is the reason for that. Even if you can maybe observe the signal a couple nights a year, you can't do it cleanly. The ionosphere doesn't, in between opaque and transparent, there's still refractive and turbulent and scintillating, and it's a huge challenge. It's not just magically the ionosphere is a problem or it isn't. And so I think to go after these really high redshifts and to get the amount of observing time you need, an instrument in space. It may be the design is build, the SKA times 5 on the moon. It could be the technology just kind of scaled to longer wavelength is what you want to do. I suspect that's not the case, but so I would say there's a tremendous amount to be learned from the ground-based experiments, but fundamentally, they can't do the science.
Yes, thank you, John. Wonderful. Colleagues, let us, I guess we should wrap up. Okay. Many thanks to all the speakers today. That was a great session indeed. Thanks to all of you. This is the second and the final block of radio astronomy in space. Have a wonderful Friday, which is the final day of Marcel Grossman meeting. And see you at the next meeting, which at least for some of us will be just next week. This is crazy summer indeed, guys. Have fun and have a wonderful weekend. Goodbye.
Thanks, everyone.